Okay, well, we will go ahead and get started now because, as I said, we do have a lot to cover today, and we're going in a different direction now. The past couple of days, we were using OpenMP, and then as we found the fairly related OpenACC approach to leverage a whole lot the hardware within any given normal computing node that you might have, be it your laptop or your cell phone, but more likely a workstation in your department, or maybe a node in a serious supercomputer. But now we want to scale beyond a node. And as soon as you want to scale beyond the node, you find that the only alternative is serious. And we'll talk about some other alternatives actually in the outro talk. But the one that's used by 99+% of the things that you're going to find running at scale is MPI. And so that's wonderful in the sense it means you only need to know one thing, but we're going to find out that it does require a little bit more effort and a little bit more of a commitment than using OpenACC or OpenMP. It's in a different way of thinking about how we're parallelizing our codes. So again, it's great because it's dominant. It's dominant because it works well and it scales well and it's been around a long time at this point. So there's no problem finding lots of libraries or algorithms that are written using it. It's ultra scalable. If the reason people are building machines with 10 million cores now are because MPI can run at that level. That's the way they are running at that level. It's extremely portable, as are really all the standards we've talked about thus far. You can run this on your laptop as well. So you have no problem running MPI codes we're going to do in this workshop right now on your laptop. It works with the other things we've been talking about. So we'll tie it all together, and when we're done, we'll have a hybrid computing talk, but we'll find that everything just kind of magically fits together. There's not a whole lot to talk about in the talk other than, yeah, this stuff just works. And that's because of serious effort to make sure when they design these standards that they do interoperate. Everything must work with MPI if you want it to scale up. The fact that we're going to have to explicitly think about our code and how we're breaking it up in a certain way is a plus and a minus. It's a minus in that it takes a lot more effort to do, as we're going to find as we get into our examples, but it is a plus, and it means we're done. We've got a code that is laid out for scalability to as a larger scale as we want. We'll see what that means. That's hard to really understand until we start to do some simple examples, but we're going to start doing that. So this is a very, very good investment in terms of learning if you want to do any kind of scientific or scalable computing, because you don't have to worry that it's going to be replaced by something else or go out of style. It has a lot of momentum, and furthermore, those exascale machines that we were talking about in the intro talk, they are all built around the idea that MPI is going to be the default way that people will scale their codes up. And any machine that we're discussing now about building 5 or even 10 years out, the starting point is, well, first it's got to run MPI. We'll see what we can do after that, but first it's got to run MPI. So your future is assured. Now, as per our tradition here, we're going to start out by just basically defining what MPI is, and then we'll pick apart that definition to try to bring some specifics to it. And MPI stands for the Message Passing Interface Standard, and it's a library that allows you to do problems in parallel using message passing to communicate between processes. Now, the big feature about this, big difference from what we're doing earlier, is this is a library. This is not a new language or extension on the compiler like with the directives. This is simply a library. And when I say simply, I mean it's like every other library that you use, whether it's a graphics library or math library. It's just something that you bring in a header file, you link in with your code, and it works like that. It works with whichever language you're applying it to. The two official languages for MPI are C and C and Fortran 90. Or Fortran, I should say, C and Fortran. However, it's been ported with wrappers to virtually every other interesting language out there. But we're going to, once again, stick with the C and Fortran since it's the official specification. But it's just a library, so there's no extension to the language. So it doesn't require you to learn some subtleties, which anytime somebody extends a language, they act like it's simple. We just added these 2 keywords or something. And then in reality, there's always a lot of implications. Nice thing about a library is we don't have to deal with that. So you can still use all of your knowledge about C or Fortran. You can use the debuggers that you use and the other libraries you use. They all are just instantly compatible. That's part of the success of it. We talk about message passing, and it sounds kind of abstract. In reality, is we're quickly going to find out that just means we're chunking or passing around chunks of data. Usually arrays, big arrays and large arrays, like in our Laplace code, we're going to find ourselves passing around chunks of that array. And we talk about using it to communicate between processes. We talk about communication with MPI. MPI takes all of those networking and hardware things that we talked about in the intro talk and makes them go away At least in the sense we don't have to worry about what our network is or our communication network is. Somebody builds these days networking systems or networking cards and hardware. They make sure it works with MPI properly and efficiently. And so your MPI calls are going to be efficient using whatever kind of network you've got. Now, the actual design of the network can have performance implications. Some networks are faster than others and work better with some applications than others, as we discussed in our intro to parallel computing hardware discussion. But MPI makes, at least from the software perspective, it makes it all look the same, and it will give you good performance on any network. It's nice to not have to worry, did somebody implement MPI well on this networking card or whatever, because it's taken seriously. The answer is going to be yes. And it's used to communicate between processes. Now, this is something that at this point in time, we actually know what that means specifically. It means that it's some kind of simple independent program running away on one of the nodes. In other words, your laptop, we've mentioned multiple times now, has 100 processes probably or more or less running on it right now. Some of them the virus checker, some of them are your web browser, some of them are your music player. That's what MPI does. It communicates between these processes because the processes don't share memory. As we talked about with our OpenMP, processes have their own independent memory spaces. They're completely isolated from each other so that if one of them crashes or does something really stupid in the code, it can't affect the rest of the machine. And that's different from, say, threads, which all share the memory, right? So the process has complete isolation, and you need to do something explicit and special to communicate between them. Well, MPI is a nice, very convenient, straightforward way to communicate between those processes. So sometimes they might be on the same machine like your laptop, but the capability of MPI to reach between devices over the network is what's going to be different than everything we've done so far. Everything we've done so far, OpenMP is used to communicate between threads on the laptop, and we have another landscaper passing by, so apologize for the noise for a moment. Hopefully it will be gone quickly. So threads are used to communicate between things that share memory, and MPI is going to be used to communicate between things that don't share any memory at all, processes. And again, we're going to do plenty of examples here, a lot of examples. We're going to do more examples than we did with our earlier things, because we're going to work our way up from some very, very simple things all the way up to eventually on the POS code again. But we're going to take a lot more steps to get there. So basic MPI needs to be able to do at least a handful of things just to get us off the ground, one of which is start processes, send messages, receive messages, and synchronize. If we can do these four things, we could, construct just about any code there is, or implement any algorithm that there is at the very least. Now you might say, why are there so many other capabilities in the MPI library? We're going to find out that most of these are just variations on doing these things in ways that make life more convenient and easy for us. So if you've looked at the MPI index or library, or you just now are becoming aware of the fact that there are so many MPI functions, you might initially be very intimidated and think, oh, geez, that's an awful lot to learn. We're going to find out that's not the case at all. There are just a lot of convenience functions that are variations on doing these four basic capabilities. And by the end of this afternoon, you're going to know how to do these basic things to the point where you could, potentially build, again, just about any algorithm you'd like. And then tomorrow, as we get into more and more advanced stuff, and incrementally as we go, we're going to roll in more and more of these other functions. And you'll go, oh yeah, I get it. This is just a slight variation on what I'm already doing that makes life a little easier in these circumstances. And so they'll tie together. You'll find out it's not 400 different drastically different functions. There's really only maybe a dozen families of functions that really do most of the stuff. And we will go over it all before we're done. Okay, but on to some actual examples here to make this less abstract. And the first example we're going to do is the Hello World program. And Hello, or executables in MPI, are run at runtime with a command that's not technically part of the standard, but you'll find is pretty much everywhere, called MPI Run. And MPI Run says at runtime how many copies of this program to run. And this might not seem that alien to you, since we know with OpenMP, for example, at runtime we specify how many threads we want our program to run on. So you can write a program that's totally agnostic as to how many versions it's going to be running, and then at runtime the user gets to pick how many copies get run. And MPI Run is the command to launch things. So MPI Run -N8, for example, says run 8 copies of this executable, and each one of them is going to say hello to us. So again, this sounds kind of similar to what we did with OpenMP, but the approach, the way that we think of these programs is very different than OpenMP. So this is where we have to change our mindset as we're using MPI. And this is going to be the hardest concept to click for everybody, but once it does click, you're going to have no problems with MPI because it's very elegant and it always sticks to this kind of mindset. But anyway, let's take a look at what that new thought process, this new paradigm really looks like. So here's our Hello World C code, and it's got some stuff in here. We're going to pick our way through it, and we'll pick our way through each one of these features piece by piece. So we'll come back and look at it. And here's the Fortran code to do the same thing. And we'll do C and Fortran once again, as we've been doing for everything, no big deal. And before we pick our way through the individual things here, let's take a look at some general MPI guidelines we'll find in any of these codes here. First of all, because MPI is a library, it has a header file. So whenever you're writing an MPI code, you include this MPI.h, or for Fortran, MPIF.h. And that means that all the stuff that we're going to use will be defined, and when we link it in, it's going to be, well, defined. So this is going to be in every MPI program we have. Now, the MPI calls themselves are very easy to spot. Everything in an MPI library is MPI underscore. And so this, all the MPI init here, MPI underscore init, MPI com rank, any of the macros or constants or the variables that are used for MPI specifically, or the definitions and declarations, they're all MPI underscore. So it's very easy to see that, and we've got some of that in our code. Most of the MPI routines return an error condition. They let you know that they worked or not. This is true for lots of library routines, and just like for lots of library routines, many of us will skip checking those error conditions. So we will very often decide to be a little bit lazy, and in my examples indeed here, I am going to intentionally, landscaper's going by in the other direction. Hopefully they're gone pretty soon. Hopefully, you do occasionally check error conditions when they might be relevant, but like many of us, we're kind of lazy and we don't check error conditions all the time on every routine that returns one. And indeed, in my examples, I just don't want to clutter them up by checking the error conditions on everything that gets returned, so I'm not doing that. However, if we wanted to, we could say error equals MPI init, and we can make sure that this MPI init routine functioned properly. So be aware of that. Now in Fortran, because Fortran Fortran calls don't return a value, there's the error parameter is stuck on the end. Instead of being a return value in C that we're usually not even looking at, in Fortran, we stick it on the end as the last parameter. So as we go over all these Fortran and C examples, you notice that the calls are exactly the same, have the very same arguments, only difference being that the Fortran MPI routines have one extra parameter on the end to return the error code. So that's a pretty general pattern we'll keep seeing over and over. Now the routines that are actually in the simple hello world code, and again, we'll keep stepping through it piece by piece here, are some boilerplate things you're going to find in every MPI code. The first one is MPI init at the top of our code here. MPI init basically sets up the MPI system. And on some machines, depending on the way they're configured or administered or the MPI version, that might have some work to do. It might have to start up some daemons or services in the background. On other machines, like on bridges, it doesn't really do a whole lot. But in the event that there's any setup to be done, that's what MPI init does. So MPI init is in every MPI code. It's the first MPI routine. It doesn't have to be the first statement in your code, but it needs to be the first MPI routine in every MPI code just to set things up. So you'll see that in every MPI program. Likewise, to shut everything down, and that's some platform dependent thing that may have a lot of work to do to clean things up, or it might not really have much to do at all, there's an MPI finalize command. And that should be the very last MPI call in your code to clean things up. So we'll find every MPI program has MPI init and MPI finalize. So those are not interesting, but they're everywhere. Now in C, one little detail here you should be aware of is for C programmers, MPI init likes to get the argc and argv commands. If you're a C programmer with any experience, you know what these are. These are the command line arguments. If you're not a C person, I'll briefly explain what they are here because you'll see them in lots of C programs. This is where the command line arguments that a user types in. So if you write a C program and it's meant to take additional arguments when it's run, as many programs are, right, have the options you can type in when you run it. This is how C finds out about them. It gets pointed to them here. MPI likes to know about those as well, so it can let all the other nodes involved know if the user added any command line arguments or some things like that. So you pass along to MPI init these argc and argv things. And again, if you're new to C, don't overthink it, just cut and paste it like this and it'll work fine. So this is pretty much every MPI program is going to have these basic things in it. And our Hello World program is no different. Now, our actual guts of our Hello World program, the thing that is interesting is where it prints out hello from. And in here it says hello from each one of the nodes. or the PE numbers. Remember, PE is a term that we'll use a whole lot, a processing element here. And the PE number, or the processing element, the process that's involved right here, each one of them gets to say hello. And when it actually runs, this is what happens. So this is the concept I said needs to click in your head. And it is very, very simple. But for some reason, not for some reason, I mean, it's natural for people to overthink this. And MPI, when it runs, it's quite simply does nothing more than make copies of a regular serial program, your MPI code that you wrote. Your MPI code is just normal serial C or serial Fortran, or potentially other languages as well, just a serial program, and MPI just makes copies of it. So when we type MPI Run -N8 for a.out, it's going to make 8 copies of our Hello World program and start to run them. That's all that happens. 8 copies of our program run, and then each one of them gets to say hello to us. It's that simple. There's nothing more to it. They're not coordinated in some magical way. They're not connected to each other in any way other than MPI calls we might start to add to communicate between them. It's just starting 8 copies of a program and running them simultaneously. Let's see. We'll come back to all these questions in a little bit because they're all relevant to what we're talking about right now. So basically, if you just keep life simple in your head, realize that MPI programs are just copies of the same program running, life will be good. And here's the picture I suggest you do to help with that. The picture that a typical MPI cluster, built in a department somewhere where somebody recognizes, hey, we have a lot of unused machines sitting around here. I'm going to build my own compute cluster so it can run overnight and I don't have to share it with anybody. Looks like this. It's just a bunch of workstations stuck together with some Ethernet in the background. So these are just 8 or 16 workstations here with some Ethernet connecting them. And so that's that simple. That's what an MPI cluster looks like. And when we run MPI programs on here, this might be PE0 and this might be PE1 and PE2. And when we run 8 copies of our program right now, our Hello World program, it just runs on 8 of these workstations. And each one of them is saying hello to us. It is that simple. Don't overthink it. It's not, one CPU somewhere, doing something. It's just 8 workstations connected together with a network running our Hello World program. Keep this picture in your head. When we get, on bridges, yes, these happen to be, each one of these is a fancy blade inside of a cabinet somewhere. The network is much more expensive InfiniBand. On your laptop, these might actually be just individual cores. But if you keep this picture in your head, from the programming perspective, it's all the same. Performance varies, of course, will vary a lot more if you're on a high-end supercomputer. But from the programming perspective, the program ought to run functionally exactly the same. So keep this picture in your head as we do things today. Whenever there's a temptation to look at an MPI program and think it's some fancy parallel thing, they'll realize it's just a piece of serial code that's run on different workstations. It's that simple. Okay, so in this particular program right here, our Hello World program, there's not a whole lot going on. We said there's this init and finalize that start and shut things down. There is one MPI command in here that is slightly interesting, and we'll find it on every MPI program, and that is comrank. And comrank is the way that a PE, one of these workstations, for example, in our previous slide, finds out which number it actually is. MPI programs, the only difference between the nodes when they start up is each one is assigned a number from 0 through whatever. And this is how they find out what their number is. So there are 8 copies of this starting up on our 8 separate workstations. And this is how workstation 3, for example, finds out, oh, I'm number 3. And then when it prints out hello, it knows its number to print out. So this is the unique numbering for every PE. And in every MPI program, you'll see the PEs need to figure out who they are to see how they fit in the organization. So that's our Hello World program as it runs. It starts up MPI, finds out who it is, prints out its PE number, and then calls it quits. Now, it's nice also in that all the I/O goes back to the terminal you launched it from. That's pretty much the job of MPI Run, the runtime system, to collect all the standard input and output. That is a nice feature of MPI that you'll find everywhere. And in reality, you mostly care about disk I/O when codes are serious, right? They're not spitting all their I/O back to you. They're writing to disk systems. That's usually just a nice shared disk system like we have on bridges, or like you might share a disk system on your cluster. But in our case today, for our examples, we'll be spitting stuff out to the screen and reading it in from the user. And MPI makes sure that stuff goes, from all the nodes to the screen and from any user input to the nodes. So that's all there is to it. There's a tendency to overthink it. Now, when I say all the nodes really run the same code, this right away, people start this is where people start to get a little bit suspicious that I'm oversimplifying things, and I'm not. Because if they're running the same code, how does any work get done? Well, we can have a piece of code that looks like this. It says, if I'm PE number 0, then play Space Invaders. If I'm PE number 1, crack some passwords. If I'm PE number 2, do this weather forecasting subroutine. So this is one big piece of code, but the PEs are all doing drastically different things, right? So there's no problem with saying all the PEs are running one piece of code and they still can do different things and go off in different areas. I mean, this is a ridiculous extreme example of it, but it's certainly possible, right? So saying all of them run the same code is not a limitation. They're not all on the same line in the code. They're not all doing the same thing at the same time, but they are all running the same a.out, and that's perfectly fine. We can be as flexible as we like. Now, in reality, we're going to find out that codes really practically kind of start to organize themselves. We'll find our examples kind of start to organize themselves very often into a pattern. It's like this, where is if you're PE 0, and there's always a PE 0, so it's often designated to be kind of the manager. And usually there's a special PE. If you want to communicate with the user, it's nice to have one PE ask the user, hey, how many iterations do you want to run? You don't want all the PEs having to ask the user that. I know you might have one PE that's responsible for printing the output. What iteration are we on if you want to print some output? So very often PE 0 gets a kind of a special role, where the other PEs do all the work and all the number crunching. They might be the worker PEs. So this manager worker pattern is very common. And again, we'll find our code just kind of falling into that pattern. Whereas our hello world code is the very trivial, just everybody's doing exactly the same thing. Yes, that is true for hello world, but we're going to find our real codes very quickly start to turn into something that looks a little bit more like this. So the analogy I want everybody to remember, to keep in your heads as we do stuff today, is that an MPI program is like if you have a group reading a book. We've got a book group reviewing books. We all have the same book. We're all decide we're going to review a particular book. But it doesn't mean we're all, so if we hand out the book and we're going to do it in real time, we're going to read through this book in real time and evaluate it. So I hand out the book and we start. I would not expect that every person's on exactly the same line at the same time. Some people read faster than others. Some compute nodes are a little faster than others. Maybe they could even have different hardware, but maybe they've got different things going on in the background, and they get different interrupts at different times. So I don't expect everybody to be on the same line. And that's true of an MPI program. When we start up an MPI program, and they all start at roughly the same time, but they can all be in different places at any point in time. So it would be silly for me to ask the reading group, say, what line is everybody on? It's like, well, everybody's on a different line in a book, and that would be true of an MPI program. And furthermore, the books might even be like these choose your own adventure books. Maybe many of you have seen in the past where you get to, on one page, it'll say, if you want to fight the bear, turn the next page. If you want to run away, turn to page 16, right? That's what MPI programs really are typically like. They've got branching and if-then statements in them. And so the PEs can each go a different way. So it's kind of like a choose your own adventure book. And so asking people what page is everybody on makes even less sense then. People may have gone off in different directions. And so that's exactly how MPI programs work. So hang on to this analogy. This is also true of the variables. Every one of our MPI copies out there has its own variables, its own set of memory, and it has a copy of the variable. So if there's a variable X, every PE has its own X. And one PE may have set X equal to 2, another one may have set it equal to 6. And so that would be like if I asked everybody to rate the chapters in the book. At the end of a chapter, put a number there, say how much did you like that chapter. It doesn't make any sense to say what is the rating for the chapter. Instead, what is everybody's rating? Everybody's got their own value for that variable. That's what MPI programs are. So the idea is we've just got copies of a normal serial program running. That's what MPI starts with. And MPI will give us the ability to coordinate and kind of keep them doing something useful, herded together. But by default, they're just independent programs. And that's what our hello world program is. Okay, let me take a second here and catch up with some of the questions. Let's see. So MPI is a communication protocol that cores universally follow. Yes, it is. It's a communication library first and foremost that is very standardized. So with MPI, there are multi-threads that are spun or multi-processes. Each one of the MPI endpoints, the programs, is its own separate process. Now, those processes are allowed to use like an OpenMP and spin off threads that they want. We'll talk about that with hybrid computing. We won't get that fancy with our early examples. We'll get that when we talk about hybrid computing later. I'll show you some examples of that. But each one is a process. They're isolated processes from each other. And so that's MPI's basic building block. Again, processes are allowed to use GPUs and attach to GPUs and are allowed to spin off threads. By default, MPI is, each one is just a separate process. Let's see, some version of MPI should be TPI encoding. MPitch uses a bunch of different protocols under the hood. It definitely uses InfiniBand, probably in most implementations, directly with verbs. But at any rate, MPI version, there are different MPI versions. Every MPI version supports multiple communication protocols. And so you don't worry about it in your MPI program. So our MPI programs will run anywhere MPI is installed and use whatever communication protocols are installed there and networking hardware. That's what makes the programs portable. MPI hides all of that from us. Let's see. Can you individually tweak the distributed programs? And the answer is no. They're gonna be copies, exact copies of each other. Now it doesn't limit what they do. We can go off. So let's say you decided that for whatever reason you decided that you wanted each individual PE to do very different things. That's fine. As we saw, we can have them each branch off into different subroutines, be doing Space Invaders or weather modeling. Our CW rank and my Fortran. So CW rank, whatever you're referring to, is not actually an official MPI call, but there are many things like boost and whatnot in Python that have bindings to it, and this looks pretty much like it's one of those. And where rank is often what grabs the PE number. So in boost, for example, there's a rank call that grabs the PE number. And I think that's what you're referring to. But the official MPI calls are the official specification are always MPI underscore commands. Let's see. Where do we find the MPI.h file? When you set up when you open the MPI module, or when you load the MPI module, like we have loaded for us. So our MPI module is already loaded because we set that up on the first day of the workshop. That means it'll find the header file by itself. So like any library, when you want to use it, you need to make sure it can find the header files and it can find the linkage properly. That's all set up by loading the module. And that's true in a lot of environments. So most MPI installations, once you've set them up, everything using the MPI wrappers like we're using here will take care of all that for you. On the MPI numbers assigned by the code, it's a property of the PE itself. The PE numbers. The PE numbers are assigned at runtime by the MPI system. So at runtime, the system gets to label the numbers. And you should think of it, by default, it'll be random. It's just free to label the PEs. And if you run again on the same hardware, it might change the order that labels the numbers. Now, because sometimes you want them to be attached to certain hardware, stay in a certain order, have a certain topology in a network, MPI has the options to control that if you want to. So there are options to MPI Run where you could designate, I want this core to be PE1, or I want this laptop to be PE1 and this laptop to be PE2. You can control that, but by default, you often don't want to. On bridges, almost all codes that run on bridges say just, hey, system, just assign me whatever PEs and label them however you want because they're all the same. And that's the normal default, but you can control it at final level of detail if you want to. So should I load my compiler script, for example? Well, don't get ahead of me yet. We haven't covered compilation, everything yet. We'll get there and you can compile the examples. I'll show you how to do that. So just like containers for code, no, it's definitely not like containers. Containers have lots and lots of underlying stuff going on them between namespaces and C groups and everything else. This is much, much cleaner than using containers for anything. And okay, so anyway, keep this analogy in mind, is that, you know, it's hard to do this first because so many of us, you know, you spent your programming career so far, you know, looking at a program and it goes line by line. And now we're starting to say, no, we got 8 programs, each one going line by line. They might be on different lines. So we'll do exercises and it'll start to click, but that's the hardest thing to kind of break away from, is to not think we have the program is on line 4. No, the program's not on line 4. We have 8 PEs. They might all be on line 4, but they might not be. So, okay, one other thing, the last thing in our Hello World program that we haven't covered yet is in this com rank routine, which gives us our PE number back, there's one more parameter that I haven't discussed, and that's com world. And this parameter is known as the communicator, and it's going to be in many, many of our MPI routines. And we'll get more comfortable with it as we go along. This is reflects the ability of MPI to divide up the PEs into a bunch of different subsets. We'll find that there are lots of algorithms where you say we have a weather code. We might want some of the PEs to be responsible for land-based weather modeling. We might want some of them to be responsible for the ocean, and they might have some different things going on. And we can divide our PE pool into different subgroups. And it's a common enough thing to want to do. Communicators allow us to do this in a nice, efficient, and clean, and elegant way. But for our early examples, we're not going to want to divide our P's up. We'll have them all doing the same thing. Like our hello world code, they all just said hello to us. And there are many, many codes that's, the PEs all just do exactly the same thing. And so if we're not going to do any fancy subsets, wherever this communicator parameter is that says, hey, how do you want to divide the PEs up? We'll use the placeholder, the MPI provided placeholder com world. So MPI com world is this predefined thing. And whenever you stick it in for a communicator, it just says use all the PEs. And that's what we're going to do here. And we'll do in our early examples. So that's the last missing piece. And then if we go back and look at our hello world program, we now understand everything going on. So briefly, we've got a header file to define MPI. We've got MPI init to set things up, and MPI finalize to shut things down. We've got com rank to find out which for each P to find out which PE number it really is. And then we got the actual code that we care about, which is to print out hello. So that's all there is to hello world. So I hope you can line by line kind of see what's going on, but we'll do some examples to more settle in exactly, this concept again of exactly what's happening when we run it. But to run things, we do need to compile them first. Now, as I said, MPI is just a library. So you could use the straight up MVC or MV Fortran compiler here, or any compiler you've got around. And it wouldn't be a big deal here. We could just say NVC, and then we'd have to type -L MPI to link it with the MPI library, and everything would work fine. However, it has become very standard over the years that when you install MPI, it also installs a nice little wrapper over your compiler to automatically link things and and set up the environment with paths so it defines the header file and whatnot. And these wrappers are pretty standardized. They're called MPI CC for C and MPI F90 for Fortran. And so this is not just the NVIDIA compiler or our local installation. This is pretty universal. And if it weren't here, it'd be no big deal. You just have to link in the library separately. But you'll find this in make scripts where lots of programs use MPI. The make scripts just assume that this is how you build everything. It's just MPI CC and MPI F90. So we'll use that convenience ourselves. But don't get fooled and think this is a special parallel MPI compiler. This is our generic C and Fortran compiler. It just makes life slightly easier. So that's how we'll compile our code. Is we use MPI CC and MPI F90. And when we run those on anything that we write, we will find we get an a.out, our usual output from the compiler. And then we're good to go. We'll have our a.out we can use MPI Run on. Here's our MPI Run after we compile our hello world program, and this spits out hello from everybody. Now, this is almost what we wanted, hello from 0, 1, 2, 3, 4, 5, but not quite. Things are out of order here. And the first thing usually comes to mind, people say is, well, hellos are out of order. Well, why would they be in order? Because again, we're just launching 8 copies of this program. PE0 is nothing special, really. There's no reason it gets to output first. They're all just writing back as soon as they get to that line of the code where they're printing stuff out. And so in this case, they happen to be in this order. If we run the same code again, they might come back shuffled in a different order. And that wouldn't surprise us, and that's no big deal. If we want to put things in an order, we'll find out how we can start to enforce some ordering with synchronization and whatnot. But by default, there's no reason things should be in a particular order because we're just 8 PEs running along, running this program, and they come back in whatever order. So let's take a pause here before we move on to our next example where we actually start sending some messages, because it's the one thing we haven't done so far, right? We're not actually doing any message passing, and make sure everybody's comfortable with this concept. So I'm going to force a pause even if there aren't questions. I'll answer any questions there are. But we're going to take 30 seconds. Make sure you kind of get how we get from this code to the end result of this hello. That's, if you get this, you're on your way. Everything is building on this from here on out. Okay. Let's see. What if we ran the code without MPI finalizing it? I mean, in reality, for most systems, MPI finalize doesn't do a whole lot, maybe flushes a few buffers, so maybe nothing bad would happen, and but maybe it would leave the last output data you had would never get written to disk. So there's no, you want to put MPI finalize in there. It's just bottom line, you're supposed to do it. You may or may not pay a price if you didn't do that. Communication network is the bottleneck. Well, it could be. We're going to find out as we start to write some real codes here. Sometimes it's computation, it's the bottleneck. Sometimes, there's more computation. Sometimes it's communication, it's the bottleneck. It depends on your code and what it's doing as to where the time gets spent. Sometimes we try to eliminate that bottleneck by overlapping our computation and communication. So whichever's the bottleneck doesn't pay as much of a price, but it depends on what we're doing. Was it printed on node 0? The output goes back to wherever you launched MPI Run for. So MPI is nice about that. Wherever MPI runs from, it'll collect all the output back there. And sometimes on bridges, for example, that might not be any node. It's not any of the nodes. It's the login node. If you run something for a login node, for example, it'll go compute nodes, but you shouldn't do that. And actually, our login nodes will forbid you from doing that. But it does need to be any of those. It's wherever you launch MPI Run from is where the output comes back to. What wrappers are. A wrapper is basically just saying it's a simple little script that just sets some things up before it calls the real program. So in this case here, the real compilers we're using, which are the NVIDIA compilers today, the MPI, so MPI CC, basically just a real simple little script. If you actually go find MPI CC, you'll see it just makes sure the libraries, it sets up the libraries, make sure the paths are set right. Just the basic things, save you from having to type that stuff into the command line if you were to use MVC compiler. And so it just sets that up and then calls MVCC to compile things. So wrapper is just a way of saying you got a little bit of code around some other code that usually sets some things up. You understand how MPI Com world works exactly? No, at this point in time, we don't have anything. It's not doing anything much, so it doesn't. We'll get into communicators a lot more, and it will be clear. Just think in terms of if anytime we're just addressing or using all the PEs, it'll be MPI Com world. So don't overthink MPI Com world. I would have just ignored it if I could get by with it, but I don't want to do that. I want to make sure you understand every byte in here. But Com world is very ignorable for now, so ignore it. And then it'll become clear as we start to use the communicators, what they do. But at the moment, it's not doing anything really. Can you explain the argc and argv parameters in C code? I really don't want to spend a lot of time on them because they're boring and they're standard C. So in standard C programs, this is just how it gets command line arguments. So if you're a C programmer, if you write a C program that says multiplies two numbers on the command line that the user types, and you might make a program called multiply. And the user's supposed to say multiply 8 and then 7. So it reads those two numbers into multiply and spit an answer out. argv and argc is how it would read from the user 8 and 7. We get put into this. So it's very boring standard C stuff. And our codes that we're going to use today, we're not going to read any command line arguments in. The programs we've used so far, we've written don't read command line arguments in, so we don't care about them. We're just going to ignore it. But MPI just wants to be aware of what they are. So actually, in the latest versions of MPI, it's now become optional. You could leave this out. And I may start to edit it out of the lectures just because I don't want to get into the boringness of it. But a lot of existing MPI codes leave it in because why not? It's safe for older codes, so you'll come across it. But again, it's just a boring C topic. And that's all. This is passing in the command line arguments. So there's no need to declare the type of return variables in C functions. Yes, there absolutely is. C functions have a return type defined in their declaration very clearly. And so main's an exception where for legacy reasons, it will default to int. So if I were probably being a little more pedantic, I might define it, but it'll default to int functions in C. But C has very clearly defined return types. Let's see. Multi-process printout. Are there any racist problems? So if we're doing a lot of prints, this is a race condition. When I said the hellos come back in different orders, it's because it kind of is a race condition. They're all racing who prints out whatever first. So yeah, if we don't do things, there is kind of a race condition here. We're going to find out later on, just like with our OpenMP and our OpenACC codes, we've got race conditions. We could put in barriers and stuff to control it. But by default, yeah, you're looking at kind of a race condition right here. They're all racing to spit out their output. So, and if we don't care in this case, that's fine. Explain the role of error code again. Error code, all the functions, the MPI functions return, let you know if they couldn't work for some reason. Like com rank is very simple and it's almost always going to work. But if for some reason something were broken in the system and it couldn't assign PE numbers, error code would be how MPI would say there was an error happened here. So in C functions return by default error values. And so we could check them. We could say if we wanted to, error equals MPI com rank. We're being lazy and not cluttering up the code, so we're not doing that. In Fortran, you don't have the option. If you want the error codes are just stuck on the end as a parameter. So, and again, as we do more examples, you'll just see error code stuck on all the end of a lot of these things, and it'll become clear. It's not doing anything super deep. After running MPI Run, you got to say your tech. Yes, well, first of all, don't get ahead of me. And second of all, as I said, you can't run things on the login nodes. So you need to be on an interactive session before we do that, and we'll get there when it's exercise time. if you put in my PE number after MPI init, would that mean all P's are the same PE number? So if you define the PE number after MPI init, so this is the definition for int MPI. My PE number is just the definition. It's not the call. But if you called if you called com rank after MPI init, which is exactly what we're doing, all P's are the same. So I'm not sure what your question is right here. We'll come back to it. So is this anyway similar to MQTT? Do you not know what MQTT is? You have to tell me. We're going to try to create Chapel language. We'll talk about that. It's a PGAS language a little bit at the outro talk. So PGAS languages like Chapel or X10 is probably the more popular version of that, are things out there that people are attempting to use. They've been around for a long time. Chapel is probably at least 10 years old, maybe older at this point in time. X10 even a little bit older than that. They haven't gained a lot of traction, but people are enthusiastic. Well, we'll come back. That's the topic for the outro to computing talk tomorrow. Okay, at any rate, so I hope everybody since the questions here seem to have stabilized. I hope everybody kind of gets this, because if you do, we're in good shape. But let's do something a little more interesting now. Let's actually do some sending and receiving. It's called message passing after all. So let's do some message passing. And the actual message passing we're going to do will be pretty much the simplest thing. We're going to send a very simple message, just an integer, from PE1 to PE0. So it's going to run, we're going to assume this is running on 2 PEs. We're going to have PE2, or which the numbers are 0 and 1. We're going to have PE1, send a number to PE0, and then PE0 will print this out. So we'll introduce the idea of using the manual pages, the documents, as we go along here. I'll point you at a very nice, at a couple of different alternative MPI documents. MPI is a very mature ecosystem, so there's lots of alternative documentation. I'll give you a couple of alternatives and a pointer to more places you can find it, but here's one setup, one set of man pages or user pages that I like, and this is how they explain MPI Send. And so you should have in your browser next to you as we do MPI programming, and not just because you're new to this, but as an MPI programmer, you'll always have your browser next to you as you do things, because these commands all have a lot of parameters to them, and it's easy enough to switch or mix them up and things won't work, right? So you want to have the browser saying what are the parameters to these MPI calls. And so in the case of send, our first real interesting command, we're going to send some data. We have a handful of parameters involved. The first one is the variable we're going to send. It happens to be called in our code we're about to look at. It's called number to send. And in C, you give it the address of that variable. If you're a C programmer, that's no news, right? In Fortran, you don't need this ampersand thing. Fortran, you just put the variable here. But in C, we give it the address of the variable we want to send. Its type happens to be one integer. So we're going to find out, we need to keep track of the types of data that we send in MPI, because it's dealing with buffers of data it's sending. It needs to know exactly, the size of things, and on the other end, it needs to know the type. So when it unpacks that message, it knows what it's dealing with. So we're going to find ourselves, for all of our messages, defining the types. We say it's one integer. It could be an array of integers, in which case it might be more than one integer, but for our simple example here, it's going to be one integer. And these are all predefined MPI types, and they're all the standard things that you would expect to find, floats and ints and whatnot. We'll find later on, it's pretty nifty. In MPI, we can make our own new types. So we can send complex objects or strips, diagonals from an array. We can define all kinds of funky user-defined data types to make life easy. But for now, we'll be fine with the predefined ones like MPI int. We have a destination that we send every message to. When we're sending these point-to-point messages, they got to go somewhere. And we said in our problem, we're sending it from PE1 to PE0. So this is the PE number of where our message is going to go. This next parameter is called a tag. This is a nifty little feature that MPI has, which allows us to kind of sort different message types. In our weather code, for example, we might send messages around, some of which are wind velocities, maybe some of them are humidities, and some of them are pressures. And if we want to, we can tag all the messages with a different type. The tag is just an integer. In your code, you often assign these integers to nice variables. So we could say wind or humidity. And these different tags allow us to filter the messages we send and receive them. Sometimes it's a nifty feature you want. Other times you don't care. You're just sending some message. In our case, we really don't care, but just to illustrate it, I'll assign a tag of 10 to this message. And we could, if you don't care, just set them all equal to 0 is probably what you'll find in a lot of codes where it's not important. But if you find yourself wanting to use this feature, you have assign them the different integers. And the last thing is our communicator. As I said, again, we can work with subsets of PEs. We certainly don't have subsets of PEs in our assigned problem here, just a couple PEs sending a message. So for our communicator, we'll use the MPI com world, the default right here. And so this is our send command. Now the receive command we're going to use on the other end of this to receive this message looks an awful lot like our send command. And so that's why I say cut and paste is your friend here, because when you're writing MPI codes and when you say, I'm going to send some messages somewhere else in the code where other PEs receive those messages, you'll usually want to just cut and paste the send and then tweak it a little bit. And that will make sure that you receive a message of the same size and type, because that's very important. And that's a very easy beginner or even a common advanced mistake to make, is to not make sure that the type and size of your messages line up. If I send one integer, on the other side, when it receives the message, it needs to know it should be looking to receive one integer. If I try to receive a floating point number instead, that's going to cause problems. And so that's why cut and paste, like I said, you cut your send and paste it and turn it into your receive, and then things will line up right. So on the receiving side, we have a variable that's going to receive the data. It's called number to receive. Again, in C, you give it the address to stick the variable into. In Fortran, you just give it the variable name. It's going to be one integer. It better be one integer because that's what we sent. Now, when we receive messages, we can look for messages. We can be selective. We can look for a message from certain sources. We can say, I'm only interested in receiving a message from PE12. And then it doesn't matter how many other messages are piling up for you. You're only going to receive a message from PE12 when it comes in. In our case, we'll just take any message that comes in. So we can use the MPI wildcard kind of for the receive, which is MPI any source. So this says receive a message from any source. Likewise for tags, I said we can use tags to filter message types. And so we could say we only want to receive a message with a tag of 10 because we sent it with a tag of 10, or we can be a little more promiscuous and just say, receive a message with any tag. So combination of these two, this is kind of the most promiscuous receive we could have. We're going to receive a message, any message from any source with any tag that's coming in. We're just going to grab the next message in the queue. And there is a queue that piles up. We'll step through the details of that, but there's a queue of messages that are piling up, and your receive can be selective, or it can just receive the next message in the queue. Once again, we don't care about using this communicator function, so we'll just stick in the world communicator. And the last variable here is a status. It's a little structure that says, if you do receive a message from any source, any tag, after you receive it, you could check and see who it came from or what its tag was if you want to. So this way you can receive any message and check up some details on it after you've received it. And so that's all there is to receive. And here's how we put them together into our C code. We'll look at the Fortran code in a second. And then some questions coming in I will get to. So here's our send and receive C code. And basically it has the generic boilerplate MPI stuff. Here's our MPI header file. Here's some the variables we're going to use. Here's it calls MPI init to set things up, MPI com rank so that the PEs can find out who they are. In this case, one's going to be 0, one's going to be 1. The PE that's PE0 is going to say, okay, I want to receive a message here. And then when I receive it, I want to print it out. The PE that's PE1, so it's the only other PE here, is going to send a message. So it's going to send this one integer number to send, which up here we set equal to 42. So it's going to send this number 42, and PE0 up here is going to receive this number 42. And it's as simple as that. Let's look at the Fortran version, because all of our examples, I've made them pretty much exactly the same. MPI header file, MPI init, com rank to find out which P it is, set the number to send equal to 42. And then if I'm PE0, I want to receive a message from anybody. And if I'm PE1, I want to send a message to PE0. And it's going to be one integer. So this is all there is to sending and receiving messages. So let me catch up with our questions here. Let's see. How to send and receive user-defined types. We will get to that. It's very, very flexible in MPI, so we'll save it for our advanced stuff a little bit later because you can define very complex user-defined data types. Like I said, C++ objects or diagonal blocked diagonals in arrays, anything you can imagine. So we'll save it for later, but it's easy and straightforward, but it's got so much flexibility, it would be distraction right now. What is the data type of a communicator? Data type of it's a predefined MPI data type, so we don't have to worry about it. But if you look at it, I will guess it's probably, so it's in the header file. You can look in a header file. It's probably called MPI com type or something like that. But it's a special MPI type. It's not a generic, integer or anything. The MPI library is very well done. So everything's got its specific types to it. Also, P0 prints out. See my job. So P0 prints out the receive message, which it does here. We submitted job from the login node. Your implicit send receive from the login node. No, there's not. So the whole where standard output goes to print stuff out, it sends and receives or anything else. We just print stuff out.
John, your audio froze for about 15 seconds.
Oh, well, that's not good. So, oh, yep, and I'm getting it. I just got a message. Just got a message from Zoom saying my internet connection is unstable. Sorry about that, folks. I am on a wired connection here, so fiber internet connection. So I shouldn't be unstable, but it happens. At any rate, to repeat what I was just saying here, no, when you print stuff out to standard output or you read stuff in, it's not any message passing or anything going on. It's something totally behind the scenes that the runtime system is responsible for. So this is, you don't have to worry about sending or receiving or anything for standard input. Or if we write to disk, which is in real codes, right, is mostly you're reading and writing from disk. That's just up to the disk system, has nothing to do with MPI. We don't worry about that. That's between the PE itself and the operating system. Let's see, some more questions here. Can using MPI any tag cause problems if you want your PE to look for specific messages? Well, yes, it could, and that's why you would use a particular tag if you want to be picky. So we can be picky or we cannot be picky, and only use this if you don't want to be picky. Lots of times you don't want to be picky. You just know messages are coming in, and you don't care where they're coming from, and that's fine, or what tag they have. Other times you do. So let's see. Okay, those of you again are running examples ahead of me. I won't address those questions just yet till we're ready to start running things. Let's see, the C code of send and receive is work with more than 2 cores. This is one. Oh, so here's a good question here. What if I'm assuming, I'm making some very simple assumptions here that this is just running on 2 PEs. And as I mentioned earlier, it's MPI codes, if they're well written, are flexible and can run on any number of PEs. Well, for our simple examples, we're not fleshing them out and making them full, nice, flexible MPI programs. So it's fair to ask the question. I've hard coded kind of that this is 2 PEs. What happens if we run this on more than a couple PEs? So it's a good question. Let's take a look at this one right here, because I coded them slightly differently. So let's say we run this on, I designed it to run on 2 PEs, in which case I hope it's clear to everybody what's going on. PE1 is sending a message, PE0 is receiving it. But let's say I run this on 4 PEs. What's going to happen here? Well, let's think about it. PE0 and 1 are going to do their thing. They're fine. But PE2 is going to come down here, and it's not 0. It's going to come down here on PE2. I got to send a message too. So PE2 is going to send a message to PE0. And PE3 is also going to send a message to PE0. So if we run this on 4 PEs, mistakenly perhaps, then this code is going to have 3 messages get sent to PE0, and PE0 is only going to receive 1 of them and print it out. And then when it quits, we're going to have a couple messages just left there in the buffer that were never printed out. Which one's going to get printed? It's a toss-up. We don't know. It's going to be any one of the 3 messages could be printed from PEs 1, 2, or 3. So it's very well defined what's going to happen here if we run on more than, if we run on 4 PEs. But I didn't design the code to run on 4 PEs, but we can see exactly what will happen here if I do it. Now, Fortran one is slightly different here, and then I actually am a little more selective here. I wrote the Fortran code to say if I'm PE0 or PE1. So if I run this code on 4 PEs, it's going to behave a little bit differently in that PE0 and 1 do the regular thing, but PE2 would come down here and say, well, this isn't me. This also isn't me. And PE2 would just do nothing, and PE3 would do nothing. So they would both just fall off the end. So this one's a slightly more robust against running on the wrong number of PEs. If I run this on the wrong number of PEs, all the extra PEs will just go through the whole code, say nothing for me to do, and just quit. If I run this one on too many PEs, the C version, all the extra PEs are going to send messages to PE0. So then it becomes a lottery for which message PE0 gets to print out. So that is an interesting question, and we have some slightly different behavior between these 2 slightly different versions of the code I've coded here. Now, one question I have for everybody else out there is what happens if, well, I guess it's not fair to ask as a question, so I haven't explained it yet. With this MPI receive right here, is there a message waiting for PE0 when it gets here or not? So when PE0 is running through this code, doing its own thing here, and it gets down here to receive, is there a message waiting there or not? So I could ask everybody to do a thumbs up or thumbs down vote, but I won't. we'll just let you all think about it for 5 seconds. When it gets here, is there a message waiting or not? The answer is we don't know. I do not know. It can vary from run to run whether there's going to be a message here when it gets P0 gets to this receive. Maybe PE1 got down here and already sent this message because it's fast, the network's fast, and PE0's got other things going on in the background, and maybe it doesn't. But it's all good, either case, because these receives, the default receives we're going to start with in MPI are blocking receives. They wait until something that fits all of its requirements shows up. So a message from the right source with the right tag shows up. Otherwise, it sits here and waits for this message. And the message might be here and it might not be. There's no way to tell from this code. But either way, it'll eventually get there. We can't tell that. Eventually, the message is sent. So eventually, the message will get here. Might already be here when it gets here. So it might not have to wait, or it might wait a little bit to get the message before it prints it out. So the code is good and robust and will always get the message and print it, but we can't tell from one run to the next whether the message will be there or not. So that is something to be aware of, that the receives by default are blocking. Later on, we'll get fancy and we'll look at receives which won't block and won't wait. They'll just go on their way. But at the moment, we're going to use the simplest and easiest to understand behavior-wise ones, which are the blocking sends and receives. It will absolutely block here until the message shows up. Okay. And we'll answer as many questions as we have to about this code, because this is, if you understand this one again, you're in pretty good shape, because now we got down the sending and receiving part of MPI too. And building on this is just doing fancier versions of sending and receiving. Okay. Code is working more 2 cores. That's what we okay. So machines know the value. How do machines know the value of MPI any source? This is defined in the header file. So MPI any source is defined in the header file. Actually, it's probably got some fancy type defined by MPI. At the end of the day, I'm sure it's an integer, but this is just defined in the header file. So all the things that MPI underscore are all defined in the header file. That's why we have the header file. So everything MPI underscore, if you wonder where they're defined and what they're set to, they're all in the header file. Receive message would only print out the message from only PE1, right? Well, no, whichever one gets there first. So in this case here, if we run on 4 PEs, I don't know which message is going to get there first. If we had three PEs, PEs 1, 2, and 3 are all sending message to PE0, we can't tell which one gets there first. So the message that would be printed out by PE0 would be one of those 3, but which one, we can't tell. And it could vary from one run to the next. So if we delete MPI send in the code, will it run forever? In other words, hang? And that is exactly right. If we delete MPI send here, then the receive's going to get here and block, code's going to hang, and it just won't finish. You'll have to Control-C it to kill it. And indeed, that is a very, very common error. Probably most of you will make that error today on one of the exercises or another. You'll run the code and it will just hang. And that will be a clue that somewhere you forgot to have a matching send for your receive. And that's very, very common thing when you're writing MPI codes, is that you don't have your sends and receives match. And that's how you find out about it, is the code hangs somewhere. And today, our codes and our examples will all be simple enough. You can just stare at your code and go, oh yeah, I forgot to send. Later on, we'll see with the debugger. It's very easy. With the debugger, you can say, which line is my code sitting on? Oh yeah, this part of my code where I wanted to receive is half of an array. It's sitting there because guess what? I forgot to send that half the array. So it's probably the most common MPI error is things just hang, and that's because a message is not sent that you have a receipt for. What assigns the value of MPI any source? That's the header file. So up in the header file, it defines the value of MPI any source. Would be more robust to execute MPI. Oh, unless you mean is this being assigned a value when it's receiving? No, this is an input parameter to receive. So MPI any source is an input parameter. It tells receive to receive a message from anybody. It doesn't end up with the source. If you want to check the source the message came from, that's what status is. So that's probably the question you're asking. What assigns the value of MPI any source? Nothing, because it's an input parameter. Doesn't get a value. It tells MPI receive how to behave. And if you want to check the value of the source of the message that's received, when you receive something from any source, that's over in status. So, okay. Wouldn't it be more robust to execute MPI send before receive? Does it matter? And the answer, it doesn't matter. It's a good question. Probably lots of people wonder that. It doesn't matter at all, because these two things are going on in separate PEs in separate places, and they don't happen in any particular order. So PE0 is doing a receive. Somewhere else, PE1 is doing a send. I don't know which one gets there first, and I can't tell. And it could vary depending on from one run to the next, or whether one node is faster or slower than another because of other things going on in the background. And later on, I'll even, to help kind of reinforce the idea you shouldn't make assumptions, I'll say, I like to think of MPI clusters, not only as that closet full of old machines, but some of the machines, and it's not uncommon, by the way, people used to assemble clusters from a bunch of old junk, and they'd be different machines. Some of them would be much faster PCs than others. Some would be newer generations, and that's fine. MPI is happy to be a cluster, a Frankenstein cluster of different types of machines. So it's easy to believe one node's just plain faster than another. But a well-written MPI code, it doesn't matter. So in this case, putting the send before the receive in the source code makes no difference whatsoever the way this code runs, and doesn't tell us whether the send happens before the receive or not. Again, this is a hard thing to get out of your head. It's hard to say that the send doesn't happen after the receive, and that's not true. Instead, you think of it as one machine's doing a receive and one machine's doing a send. They're two separate machines. The send and receive never happen on the same place in this particular code. So that's, again, two separate machines. We don't know whether the send or the receive happened first. P0 enters the if conditional and goes through. We'll keep waiting for the subroutine MPI. So the send, P0 enters the if. So yeah, P0 will wait for the receive. This will the blocking receive. It will wait forever for the receive. P1 sends a message before P0 gets received. Where's the message stored? We're going to get onto those details in the very next slide. There's a message queue basically that piles up. Okay, not a good idea to write the send command early to receive. So receive cannot happen before send. No, because if writing the send before the receive wouldn't guarantee us that. If we switch the orders of these, it wouldn't guarantee us the order that the send happens before the receive, because the send's happening on a different PE. It's happening on PE1. So if I flip the order of these two lines, and by the way, I wrote them in this order exactly to raise these questions in your head. If I put the send up here first, if I say if I'm PE1, so let's look, Fortran one's a little clearer because it says PE0 and PE1. So if I flip the order of these two statements right here, if I say if I'm PE1, do the send, else if I'm PE0, do the receive, that is not going to guarantee me that they happen in that order at all, because PE0 might take a long time, PE1 might take a long time to get to the send before PE0 gets to it. I don't know that. They're two separate machines running away with two separate programs. So I can never be sure. Nothing gets anywhere. Again, it's our book club. Our book club, I can never be sure just because I wrote one line. I can never be sure that some reader isn't faster than another, and this is a whole paragraph ahead. So one reader could be a whole paragraph of another reader in our book club. It's not right to say what line are we reading in our book club any more than it's right to say what line is our program on here. We got two separate copies of the program running, and they could easily happen in one PE0. PE1 could be down here on the finalize before PE0 even gets here to sign the number to send equal to 42. It's possible, and our MPI program shouldn't care. It should end up printing the same result out either way, and it will. So I don't know that PE1, like I said, or PE0 isn't stuck up here signing number 42. Well, PE0 is already, or PE1 is already done. That's perfectly fine. And so that's the way you have to force yourself to think here. And again, that's the new thing. That's the new thing that's hard to get into your head, because most of you have spent most of your programming career talking about serial programs that, oh, I'm on line here, I'm on line here, I'm on line here. And now we're talking about two separate copies of this program. One of them might be on this line and the other one might be on this line. And we don't know. And with MPI, we shouldn't have to care. And indeed, we don't. This program will run correctly regardless of that. But that's, I want to beat this concept into your head, because that's the hardest thing to sink in. And when we get to the first exercise, you're going to revert back again to thinking, okay, I run this line, then I run this line, instead of thinking, no, I got two separate programs and they could be anywhere in this entire code. What happens to MPI receive if more than one message was sent out at the same time? We're going to cover that next couple of slides when we start to talk about the message queue. So we'll get on to that now. And this is the reason that I used to not want to dive a whole lot into what happens behind the scenes with the message queue. And then after you teach this enough, you realize that it's just human nature, including my own. You want to know what's happening with all these messages piling up, what goes on behind the scenes. So we're going to take a little detour here for the next 10 slides or so. Just a quick detour, only 4 or 5 minutes here, but I'm going to explain to you what happens behind the scenes with these messages. Now, the reason I call it a detour, and the reason I have this kind of warning here, is that I don't want you to think that you have to understand any of these details to write MPI programs and get them to function properly. This is all MPI implementation behind the scenes. And so you can't help but wonder it, and we're going to describe it. But do not think that this is all complications. You have to take notes right now and pay attention, or we won't be able to do the exercises or move on from here. This is just to satisfy your curiosity because the questions are coming in now. And I could just say, MPI just says there's a queue for messages. Don't worry about it and leave it at that. And that would be fine. And you could write correct MPI codes, but that's just it's an unsatisfying answer, right? And the questions are going to keep coming in as to what's really happening. So we're going to cover it, but I don't want you to get intimidated by these details. You don't need to know about it. So we're going to peek behind the curtain here quickly, but do not think that you need to understand this. So this is what happens when we actually send a message with our standard blocking sends and receives in MPI. Is we have some variable, and typically for real codes that you're not sending a lot of integers, you're sending big arrays. We've got a big array we want to send. It's our weather code. And so our array might be the strip of weather along the border between Pennsylvania and Ohio, two adjacent states here in the United States. And the weather is coming across the border from Ohio into Pennsylvania. And so our weather simulation needs to send a big chunk of that array from Ohio to Pennsylvania. So we do an MPI send on that array. What actually happens is it copies it into a send queue, and then it sends it across the network and ends up in a receive queue. Then eventually when the right receive comes along, it ends up being received. And the reason we have this multi-step process here, and it doesn't just try to stick it straight from here to here by default, later on we'll see how we can try to do this for efficiency's sake. But the reason that we have these extra steps behind the background is to make life easy for you. The first reason that we could take the message when we do a send and copy it to the send buffer is because if you write an MPI program and you do a send, it's nice after you're done with the send to put that out of your head and go, the data was sent. I can go ahead now and do things like maybe I want to mess with this array A. I want to start working on the next time step. I sent the data from my last time step of the weather. Now I want to start working on the next time step. So after I do my send on the data, I want to go ahead and work on my weather array. I want to go ahead and change things. And that's fine because there's a copy down here. If we didn't have this copy down here and we waited until it could get over the network, you would have to have some way of actually waiting and checking and say, has it been sent yet before I can mess with this data? And later on, we'll see MPI gives us that ability. If we're willing to take that responsibility, we could do that to save the copy and make things a little faster. But by default, to make life easy on us, MPI says, I sent the message, regardless of how long it takes to get there. It's a copy's made. You can go ahead and start messing with any of your variables, including the ones you just set. So that makes life easy for us. We do a send and we forget about it. Go on and do our calculations. So that's the first reason. But now we got this copy out there. The network has, takes time to send things. And it might be a huge message and you need to send in pieces. So it sends it over. And on the receive side, your code might be doing who knows what, be involved in a calculation. It can be slower or faster than this P. It might be waiting for the message, but it might also have other things occupying it. So it can't just receive it straight into A. It's got other things that the CPU can be doing. So the network card sticks it in a buffer here. It's stuck into this receive buffer. And it won't be received from that receive buffer. And over here, we can see RPE is on its way. It's doing calculations. It can do whatever it wants. It doesn't have to worry anymore about that message or that variable or what it does to it. So over here, we've got a receive, and it will wait until that receive, a matching receive that for that particular message is received here to receive A. And then it receives it. Now, while it's waiting to receive A, other messages from other PEs, from other states, Pennsylvania could be received messages from New York and from Maryland about the weather, could be piling up in our queue. So we have this message queue here with a bunch of messages piling up in it. And those messages each come from different sources and can have different tags associated with them. If we're not using tags, maybe they're all equal to 0, but maybe in this code, we have some tags so we can help to distinguish between them. So they're piling up in the queue. So when we do a receive, a blocking receive, it will go through that queue and look for a message that matches the source and the tag. So if I do a blocking receive and I say, I want to receive a message from source 1 with a tag of 2, it's going to go through that queue and receive this particular message right here. If I say I want to receive a message from source 4 with a tag of 6, I go through this queue, there's no message. It'll sit there and block. Even though there's a bunch of messages waiting in the queue, that receive isn't looking for one of these messages. It'll block and wait. If I say I want to receive a message from source 3 with a tag of 2, well, there's actually a couple that match that. So it'll grab the first one from source 3 with a tag of 2. If I say I want to grab a message from any source with a tag of 2, well, there's a bunch in there that match that. And it can grab any one of those. Who knows what order they came in. So it goes through the queue and it looks for messages that match the source and the tag. And that's what it will use to determine if it blocks or not. If there's one in there that fits, great, it grabs it and goes on its way. If there's none in there that fits, doesn't matter how many other messages are there, it will block until the right one comes in. Now, as I said, there are non-blocking sends and receives as well, and we'll get onto them because they are useful. In particular, they avoid some problems that can show up when messages grow very large. But we don't have that problem just yet, and a lot of you won't have that problem for a lot of the messages you're going to send. They'll be relatively small messages. But let's say we have a very large message. How does MPI handle that? If we have a very large message, the array A can easily be many megabytes, hundreds of megabytes in size. In real serious scientific codes, that's not uncommon, that these things are hundreds of megabytes or larger. So if we have an array that's hundreds of megabytes or gigabytes in size, it's too big to send in one chunk. The network and it's the way it has to break it up, and our send and receive buffers just might not be big enough. It might be many gigabytes, and we just don't have enough room in our send and receive queues. Memory is not infinite to receive it. So MPI, though, will do the smart thing. It will break the thing up into chunks of the right manageable, acceptable size. So the send will block. So you might say, why are sends called blocking sends? Because the send could also block. If the message is so huge, it has to send it in chunks. It will block until the whole thing is sent to save us from accidentally going ahead and messing with our computations after the fact before the entire thing's sent. So send will block to save us from having to worry about that. And while it blocks, it sends these chunks over. But the chunks will sit here and wait. They'll be stuck in this queue until the right receive happens. And the receive might not be posted already. The receive might not be, we might not be there in our code yet. We might still have to wait for the receive command to find that in our code. So things back up for a little while. And in a normal case, no big deal. It just slows our code down a little bit. But there is a potential here to introduce a deadlock, because what we could do is we might have two huge messages between P1 and P2 that we're trying to exchange. And that's with our weather code, that would make sense. Pennsylvania and Ohio will want to exchange these two huge messages along the border. So this PE sends this huge message and this PE sends a huge message, but this one blocks because it's so huge, it's going to block. It needs to send it in pieces. It needs to wait for PE1 to start receiving the message before it can continue. And PE1 needs for PE0 to receive its message before it can continue. So both sends up in a block, end up in a block state, and we have a deadlock. So this can happen with big messages. So we find as our codes handle big messages that we don't like these blocking sends and receives, and then we can go on to non-blocking sends and receives, and we'll look at them later. The only problem, the reason we don't just start with non-blocking sends and receives is then with non-blocking sends and receives, we'll see we're responsible for making sure that the message was actually finished sending it before we can mess with the variables. So this solution avoids deadlocks for huge messages, but it introduces a little more responsibility for us to pay attention to when things are actually sent and received. So for small messages, we don't really need this. And for our examples to get going with MPI, we don't need extra complexity. It's not an unusual amount of complexity. It's perfectly manageable, but we'll wait till we have a little more experience with MPI before we decide we want to deal with this problem, potential problem for huge messages. And right now, we're only sending small messages. So behind the scenes, again, we go back to the first slide. Behind the scenes, this is what happens when we send a blocking send and receive, and it makes life very easy and straightforward for us. It does all these details. It introduces some performance bottlenecks and deadlock possibilities, but when we get to messages that are big enough to manage that, we've got a solution, which is the non-blocking sends and receives, which are slightly more complex. So that's kind of the behind the scenes look at this. And there are also different modes of sending messages too, which we'll avoid ever having to worry about because we use non-blocking send and receive. So I won't even cover this. So that's the end of the detour. So that detour, I hope, showed you what's happening behind the curtain, because it's hard not to want to know that. But life is this simple. You do a send and you do a receive and the data moves over. So all those little things that happen in the background to make this happen and make sure it's reliable, you don't need to have in your head. You can just say, as long as I use blocking sends and receives, when I send a message, as long as I make sure someday I receive the right source, from the right source with the right tag, it'll be received. That's all you need to know. So MPI is written this way to make your life simple, and it does a lot of things behind the scenes to enable that. But you don't need to have all of that knowledge in the front of your brain as we're going these exercises or as you're writing MPI codes. Okay, let me see what questions we have here from that. If one core you're using is dying in some way, well, if it's so we'll pick apart the word dying here. If a core is really slow or one core is slower than another, then it just takes longer for that core to get around to, say, receiving that message, or maybe to sending its messages out, and your code just runs slower and it's no big deal. Now, if you mean dying in the way that a lot of people would say dying, as in something, a core actually, or a process goes away, has a problem, and fatal flaw, and it dies, a hardware failure, for example, then MPI codes under those circumstances, normal MPI codes will just crash. MPI does not have built-in fault tolerance. It assumes that none of your hardware pieces, your ranks, your PEs actually fail. And building in fault tolerance is a huge pain, and that's why we by default assume that. You can make fault tolerant codes, but you don't want to. We'll talk a little bit more about that with the outro talk. By default, you want to assume your machine's reliable. It makes life a lot easier, and that's what most MPI codes assume. So if a core actually dies for some reason, has an error and dies, your MPI code's going to crash, and that's fine. That's what most people expect. But in the case of it slowing down a whole lot, then your code should still behave the same. And you should indeed think, when you're writing an MPI code, you should think, what if one of these cores is insanely slow, 1,000,000 times slower? Later on in my slides, I say that's what you should think of, is one's 1,000,000 times slower than the other one. Well, it'll run slower, but it will still complete exactly the same every time. Whether it's PE0 is 1,000,000 times slower, takes forever to get to the receive, or whether PE1 is 1,000,000 times slower and takes forever to actually send, this code will still eventually complete. It'll stagger its way across the finish line. Let's see. But part of this question also said, could the queue end up filling with messages if something's really slow? Yeah, so if something's really slow and people keep sending in messages, the queue is going to fill up. And eventually, when the queue fills up, they won't crash. What will happen is the sends will start blocking on the other end. So if the queue fills up and there's no room in the receive buffer, all the sends are going to start blocking on the other end of it. Okay. So basic MPI send does not block unless the message is really big. That's exactly the case. So the basic MPI send that we're going to use to get off the ground with never blocks unless the message is big, in which case it will block so it can do the right thing and let the message eventually filter through. And we'll see how we can move on to non-blocking and change that behavior if you want later on. How do we know if the messages are not received and lost in transmission? MPI is assuming you have a reliable protocol. So again, MPI codes, normal MPI codes are written assuming that you've got a reliable machine. And they're built on, so the transmission protocol, so if you build your own cluster, things are going to be built on top of TCP/IP, and it's going to be reliable. But maybe for performance reasons on InfiniBand using verbs, you don't have that built in, to improve performance, and something else has to worry about, but not your responsibility. You're assuming that the machine is reliable, and that's a very sane assumption. So these codes that run on millions of cores, that's the assumption they make, is the machine is reliable. So that's the default MPI programming mindset. Will be a deadlock in the C code if we use more than 2 PEs. So we went over this, in the C code. Let's look at the C code here. If we use more than 2 PEs, this particular code, I assume you're talking about, and we went over this, and the answer is no, because the other PEs will all send extra messages, and that's fine. That's not going to cause them to lock. They're going to go into the receive queue over here, assuming they weren't huge messages, and they're not. They're just integers. So the end result of using more PEs here is that PE0 has some messages in its receive queue when it quits that never got received. So toolkit user, I only need to take care of arguments, the MPI functions you don't care about. Yes, absolutely. You don't worry about behind the scenes. As an MPI programmer, you assume the system is reliable and configured right, and your MPI programs don't worry about any of that stuff. And that's not just a theory or a nice idea. Again, that's the reality of codes that run on big machines on millions of cores. Is the MPI programs assume that the system behind the scenes worries about the reliability of the transmission. And the machines are built to be that reliable. MPI a little bit clever about breaking up large data. Does it work? So MPI by default is pretty smart about that, but you have the ability to change that behavior with a bunch of environment variables. So I won't dive too deeply into them. I'll mention them briefly in advanced MPI, but there are a bunch of variables you can override if you want to change the defaults to change the buffer size. You might say, for example, I noticed my MPI code slows down because the receive buffer fills up with messages. Why don't you make the receive buffer bigger? Well, there's an MPI variable to set the receive buffer. You can make it huge, but now you have less RAM for your application. So the MPI defaults try to say, we don't want to hog resources from the application, and we'll pick a reasonable default, and you're feel free to override that and make your receive buffer huge because your application runs on a terabyte node and your application only uses 200 gigabytes. And so you want to increase the receive buffer to make it 400 gigabytes of receive buffer. You're allowed to do that. So there are a lot of variables in MPI that you're allowed to tweak to change the behavior. Well, we're not running messages yet. Let's see, unexpected tag received descriptor. So I don't know what this message is here that you're finding and what you're running, but we're not there to running anything yet. Let's see. In the hello C example. Well then, yeah, the hello C example should work just fine. So you probably don't have the right module loaded is my guess. But we'll debug hello if you want to, if you really want to in the first exercise session. And make sure you've got your environment set up correctly, which is probably the problem. Okay, but again, we went behind the scenes and looked at how stuff works, but I hope you're very comfortable now with how this actually works and realize you don't need to know all those mechanisms to get an MPI code sending and receiving to work. You just assume that send is reliable and will send the message. You just assume that receive will sit here and wait until the message shows up that fits its parameters. And you can choose as the programmer to be really picky, or in this case, really not picky, right? We're going to take a message from any source with any tag. We're going to take the first message coming at us. And so that's all you need to know to write good, well-functioning MPI codes. Okay, with that in mind, let's go on and start to write a fancier program that does a little bit more. And then this will lead us into our next example, which is actually a nifty program that does some nifty stuff, but we'll take an intermediate step to get there and introduce the last piece of functionality that we haven't really introduced yet, which is synchronizing things. I mentioned, there's kind of 4 things you need to be able to do to make an MPI code run, complex algorithms. You need to start things up. You need to send and receive messages. We're also going to find we need to be able to synchronize things at points. And so otherwise there's no synchronization, right? I'm trying to pound it into your heads that everybody can be in a different line of the book or a different page of the book, and your codes will all be in different lines. Well, sometimes it's important to get everybody on the same line. Sometimes it's important for the book club leader to say, everybody stop at the end of chapter 1. And we're going to synchronize and talk about chapter 1. So we'll introduce that capability here. So to do that, we're going to make ourselves a little contrived problem here that's going to have PE0. It's going to run on 4 PEs in this case. We're going to have PE0 send a number to other 3 PEs. Each of them are going to multiply that number by their own PE number just to have something to do that's a little bit different. Then we're going to print the results out, but we're going to do them in order this time. So remember our hello world program, things weren't in order. And I said, why would they be? Well, now we're going to find out we can make things in order with some synchronization commands. And we're going to do that. We're going to then have the results sent back to PE0, and PE0 is going to print out the sum. So this isn't really all that profound of a task, but it's going to make us jump through the right hoops to learn these new capabilities. As a matter of fact, I have here some very faded, intentionally faded text. What we're really going to learn how to do is do some more advanced capabilities like broadcast and synchronize and reduce. Remember, reduce is a thing we've been using a lot so far. I said it will come back. So we're going to use barriers and reduce that we saw before. So we're going to learn these things, but we're going to learn them by using our basic MPI commands. So anyway, we'll come back and tie it all together when we're done. So first of all, here's the full code that does all this stuff. We're going to step through it line by line because that is the way actually that I think of the codes when I'm writing it. And you should think of codes when you're writing it too. We're going to step through it from the perspective of different PEs, the manager and the worker PEs. So here's our full C code. Here's our full Fortran code. We're going to step through them both line by line. So let's start stepping through the C code first. And we're going to step through it from each PE's perspective. Now, this is the way you want to think of your MPI codes. You want to say, and we've kind of been doing it so far, but I haven't made it as explicit because the examples didn't get large enough to be interesting. But you want to step through your code, say, I'm PE0. Here's how I run through my example. I'm PE1. Here's how I run through my version of the code. I'm PE2. Here's how I do it. Now, in reality, if you've got a code running on 10,000 PEs, you don't go through it as all 10,000 PEs, but you do go through it typically as the manager. I'm going to go through this as PE0. That's the manager PE. We're going to step through the code like PE0. We're also going to step through the code like we're one of the worker PEs, and that is going to be probably the same path in most of your MPI codes for all the other PEs. So it could be PE5 or PE12. We can step through it all. So we're going to step through the code thinking in terms of each PE just running a serial code. Again, think of MPI, regular serial codes, just multiple copies of it. So we're going to step through this thinking like a serial programmer, just a serial PE running through a serial code as PE is the manager PE or the worker PE. So anyway, let's do this. Let's do it for step 1. So we got our MPI code here. It's got our header file. It's got our MPI init, com rank, so the PEs can find out who they are. That's all generic to us now. We know that. So here's the first step that we want to do. We said we wanted PE0 to send a number to the other three PEs. The number it's going to send is equal to 4 up here. So it's going to send a number 4 to the other three PEs, PEs 1, 2, and 3. So here's PE0. PE0 says, okay, I'm going to work my way through the code. That's me here. I'm going to send 3 messages. I got a little for loop here. I'm going to send a message to PEs 1, 2, and 3. It's just this number to send. It's one integer, and I'm going to send it to 3 different sources here, 1, 2, and 3. I have a tag of 10 in here because why not? So we're going to send 3 messages to the other 3 PEs. Meanwhile, the other 3 PEs are down here in this else statement, and they're each going to receive 1 message apiece from PE0 with a tag of 10. So the other 3 PEs are each to receive messages. Are the messages waiting for them when they get there? I don't know. Maybe, maybe not. It might change from one run to the next. We don't care. But eventually, the message will get there, and eventually they will all 3 of them receive their message. So that's step 1. Step 2, after they receive the message, we said we each want them to multiply it by their PE number, just to have something different to do. So each one of them is going to get a result that's going to be a little bit different on each PE. It's going to be the number that they received, 4, multiplied by either 1, 2, or 3. Okay, that's step 2. Step 3, we said we wanted to print the things out in order. And this is where we find ourselves needing a new capability here. Because remember, our hello world, we said, was in random order. Now, what if in our hello world program, what if we rewrote it? So this is some pseudocode here. Of course, this isn't proper C or Fortran. There's a little pseudocode. So what if we rewrote our hello world program, and in pseudocode, we said, if I'm PE0, print hello from 0. If I'm PE1, print hello from 1. Is this going to print out in order right here? Would this pseudocode get us the ability to print out our hello world stuff in order? And again, I could go with the thumbs up, thumbs down, or whatever, but maybe if 1 or 2 of you chime in the chat channel, we'll go with that. But I'll let you think about it for 5 or 10 seconds. Is this going to print out in order? Think about it. Okay, well, the early answers are correct. No, we can't tell. We don't know what order this is going to be. And that's because, again, PE0 might be super, super slow, and PE5 might be incredibly fast, and PE7 might be a million times slower than the rest of them. So we don't know. So we can't tell. This is going to come out in random order. There's no way of telling. Now, what if we had a command called barrier, which we recognize as something that we saw briefly with OpenACC and OpenMP. We said it's a command that means all the PEs have to get there before any of them can continue. With OpenMP, we said all the threads needed to get there before any of them can continue. Well, with MPI, it means all of the PEs, all the processes need to get to barrier before any of them are allowed to continue. So this is like our book club. It's like me saying, everybody stop when you get to chapter 2. Everybody, no matter how fast of a reader you are, you don't get to start on chapter 2 until everybody's done with chapter 1. That's what a barrier is. Now, will this print out in order? And there's a fast typer out there, maybe. In this case, some of you are right, some of you are wrong. The answer is this will print out in order. This will always print out in order because PE, no matter how fast PE4 is and how much it wants to get down here and print out this, and no matter how incredibly slow PE1 is, PE4 doesn't get to jump past PE1. They all get down here. All 8 of the PEs have to get to this barrier and let PE0 do its thing. Then they all want to race ahead, including the super fast PE8 and the super slow PE1, but they all have to wait at this barrier and let PE1 print things out. So if we put barriers in like this, now things do have to go in order. This is just like me saying at the end of each chapter, everybody pause. Then no matter how fast somebody is, they can never get ahead of somebody else by more than a chapter. So this will print out in order. Now, it doesn't matter if one's a million times faster or slower than another. Now, I would, of course, roll this up into a nice little loop like this. So this is what I'd do if I were really writing this code. The hello world program, I'd put it in a little loop, and it's exactly the same thing. A loop with a barrier here, saying, okay, PE0 gets to go first, and it doesn't matter how fast PE1 is in going through this loop. It can't jump ahead of the barrier. There's 8 different codes running 8 different copies of this loop, but they all have to synchronize at this barrier right here. And so this is the nice way to do synchronization. So here's how we can make our hello world program print out in order. So, oh, by the way, here's where I want to introduce a quick little warning for you. This is a little bit of a digression. I don't want to kill our momentum here, but I feel necessary to point this out, is that one of the things you'll find modern computer systems have tons of buffering in them. Buffering is just a way to speed things up a whole lot. So, because if you look at you look at your laptop, if you have a program and it writes a byte out to disk, it actually has to go through so many layers of caching and everything else before it actually gets to disk. It doesn't want to write one byte at a time. It wants to gather stuff together and write a whole chunk of data at a time. And that kind of buffering makes perfect sense and speed things up a whole lot. But if you're doing a bunch of stuff in parallel and you're writing out a bunch of independent results, it can scramble the order of those results and make it hard to tell what's up. So if you actually write a hello world program, even with barriers, if your system happens to do a lot of buffering, it might actually still, you might end up with a scrambled order. So you often want to turn off the buffering if you're doing debugging or something like that to make things work right. Turning off the buffering, though, in modern computer systems is very hard to do because there's so much of it going on and the systems don't want you to do it. And so the trick, some of you who are experienced programmers might say, oh, there's a flush command to flush output to make sure it doesn't get buffered. Those things don't even usually work on most systems anymore. Even the flushes get buffered. So it's a real pain in the butt. Here's a trick I have whenever I've got output coming and I want to keep it from being buffered that I find works almost everywhere on almost all Unix and Linux systems and others as well, is instead of writing to regular output, if you write to the standard error output. So for most of you, if you're newer to programming, you don't know what this is. Instead of standard output, standard out, STD out, there's also a standard error. This is usually reserved when you want to report something's gone wrong. And because it's an error thing, most systems don't buffer it. They assume it's unusual. And so writing the standard error unbuffers output. So for any of you that start to worry about the output getting buffered and scrambled in parallel coding, here's a little cheat. It, of course, kills the performance, but it's good for debugging purposes and whatnot. It's great. And standard out error on Fortran, if you write to unit 0 like this, it'll do it. In C, if you use an fprint, a file print to print the standard error, it'll do this. So here's a little trick that I use whenever I am dealing with codes and the output's getting all buffered. So little digression, but you'll find it useful for those of you even doing some of our more advanced exercises here. If you stick in a lot of print statements to see where you are in the code and they get scrambled in order, you can fix it with this. Okay, back to our regular programming. We said we have this barrier command here, and we can stick it in a loop if we want to make sure that everything gets to print out in order. So this will make things print out in order. So here is, because this was our, fourth part of our problem here, we said we want to print our results out in order. And that's exactly what happens. So each one of our PEs gets its chance to print first, and the other PEs cannot race ahead no matter what, because they've got this barrier in the middle of the loop. And so boom, we've solved our output order problem with our new barrier command. And we got our last missing piece of functionality in MPI, the ability to synchronize things. So we can do anything theoretically now. Okay, so that was the next step. We want to print things out in order. The next thing we wanted to do is have the PE send the result back to PE0 for PE0 to add them together. So PE0 down here has a for loop. It wants to receive 3 messages. And it's going to receive 3 messages from PEs 1, 2, and 3. Actually, it's going to receive them in order here from 1, 2, and 3. And at roughly the same time, PEs 1, 2, and 3 are down here. They're going to send a message to PE0. So they send a message to PE0. PE0 now has the results that it adds together and can print out the answer, and we're done. And so I'm going to quickly step through the Fortran code because I assume Fortran people were probably mostly following me there, but we'll step through the Fortran code with the exact same logic. So step 1, we said we wanted to send a message to the other 3 PEs, the message being the number 4. And so it sends 3 messages out. The other 3 PEs are receiving that message. Each one of them gets that message, multiplies it by its own local PE number. Then we said we want to print the results out in order. Well, we've got a loop here to have each PE print its results out. And by sticking a barrier in this loop, we're going to force them to print out in order. Lastly, or almost lastly, we said we want PE0 to receive those 3 partial numbers, those 3 subtotals. And it's going to sit here and receive 3 messages from each one of the other PEs so it can print the final result out. And if you run this code, you should get some output that looks kind of like this. And so this is a code now that has all the major functional pieces of MPI working in it. So make sure you understand this. Let me see, do we have any questions here? And so the benefit having a PE be a manager type with one manager for the manager type. So if you're kind of built some hierarchy of things going on here, I honestly can't say as I've come across a code that benefits from that. So the general answer is no, that's not a generally useful thing to do. But certainly if you wanted to construct some hierarchy of managers, you could do it. MPI allows us to do that. When we get on the communicators, we haven't used communicators yet. Communicators would make doing something like that very easy to do. With communicators, we could make a hierarchy and subsets corresponding to that hierarchy. I haven't come across a code that does that, but it would be easy to do. Briefly re-explain what is buffering in the case of outputting messages. Okay, I will say it's a little bit of digression. I hate to even stick it here, but it will come up when some of you start on your own systems running using print statements to debug your code, see where it is. Computer systems just want to collect IO. So if I say print 1 and then print 2 and print 3, and this is in any language, this isn't just MPI. This is just a normal Python script you're running on your laptop, and you say print 1, print 2, print 3. Sometimes the system might decide that it should really not immediately print those out. It will gather those together into one chunk to print them out. And so print 1, nothing will happen. You'll have to wait until it says, until you print 2, print 3. Eventually it'll say, that's enough to be worth writing, and it'll print all 3 of those lines out at once. You don't often see this on simple-minded console applications, but you could see it if you're looking at writing to disk and things like that. The system just likes to gather stuff together. That's what the buffering does, to make it more efficient than going through the whole pipeline 1 byte at a time. And so that buffering means that the things just don't, you do a print and it immediately doesn't happen. And with a large complicated system like you have when you have MPI, when you start building clusters or start running across many cores or start running across a supercomputer, that buffering can mean it so that you actually said print when I get to here, print when I get to line 5 in my code. And you actually got to line 5 and the print doesn't happen yet. And it can confuse you when you're using print statements to debug an MPI code. So this just prevents that from happening if you think that your prints aren't showing up in a timely fashion. So again, I don't want to distract everybody. That's a weird platform specific thing. That's an artifact of modern hardware and the way it's put together. But here's a solution for it for those of you that use print statements to debug your code, which is a lot of people. And that's a fine way to debug. I use print statements to debug code all the time. It's not worth me firing up a debugger to get into it. And I'm like, did my code really get to that line? I'll put a print statement in, got here. Well, sometimes on systems, I'll be like, God, I know I got there. Why isn't it print? Why didn't it print out? Well, it's because it got buffered somewhere. So that's the reason I got into that. But I don't want to scare people too much. That's not an MPI topic per se, and it's just a debugging helpful hint. Somewhere down the road when you're debugging your code, print statements don't seem to be coming out where they should. The reason why you start the barrier before the condition, then after in the pseudocode slide. And the answer is no, not really. I guess it could work in either place. We could have barrier before. First, if we put a barrier before, we really wouldn't do anything useful here, but it would hurt. So we could stick the barriers before and after, or in other words, in our for loop, we could shuffle the barrier before or after, as long as, it wouldn't matter. Or for that matter, in our real code here, yeah, we could move the barrier before or after the if statement. It's still going to serve its function. As long as the P0 gets here first before anybody else can print, it'll work. Near the end, we didn't use MPI Send before P0 received the numbers. So at the end here, we have a send at the same time we're receiving, basically. So we are using send. So there is a send for this receive. This is the send that's used for this receive. Counts won't do that. Yeah, probably not. They will not do that. Yeah. Run example 2 and example 3. I don't know. I'll have to go and make sure your environment's right and go and see why can't those run. We'll take a look at we're coming up on an exercise. We'll take a look and see what's up with that. How are we doing at time? Oh, we're okay-ish on time. Does barrier wait until all the PEs are finished or just until the condition is satisfied? Barrier is very simple, so don't overthink it. Barrier waits until all of them get to that barrier. It doesn't worry about conditions or anything. Barrier is a standalone thing. All the PEs must get to this barrier before any of them can continue. There's no conditions or anything else attached to that. So all the PEs just have to get here before any of them are allowed to continue, including even PE0, right? PE0 doesn't even care about printing out its results. It still needs to get here. P's 0, 1, 2, and 3 all need to get to this before any of them are allowed to continue. So that's all. So that's the complete and total definition of barrier. So don't overthink it. All the PEs get to a barrier before any of them can move ahead. Okay. So with barriers are often necessary. They absolutely are in our code right here to have the result print out. They're also sometimes really convenient when you're writing an MPI code and you're trying to debug it and make sure that everything is, did all of my PEs get here or not? And you can stick into the barrier there to keep things on the same page, to force things onto the same page, just for organizational purposes in your head. And there's nothing wrong with that when you're developing writing code, to stick in lots of barriers to say, okay, I'm focused on this chunk of code right now. Let's get all the PEs in here, just so I don't have to think about PEs maybe being somewhere else. I can use barriers to keep all the PEs kind of on the same page as I go through my code. And that's a fine way to develop and debug a code. However, of course, those barriers could also be wasteful. I mean, every barrier means a PE is sitting there not doing anything. So having extra barriers in your code is wasteful. And so a lot of people will develop a code with lots of barriers wherever they think things are, getting tricky. And then when they're done, they'll go back and eliminate the unnecessary barriers. And that's a fine thing to do as well. So nothing wrong with that. So you don't want extra barriers in your code, but sometimes they're necessary. I mean, but you'll sometimes hear people make statements like, I don't have any barriers in my code because they just slow things down. Well, that's ridiculous. Barriers are absolutely critical for lots and lots of algorithms. That barriers are required to make them work properly. So you need barriers sometimes. But yes, you don't want extra barriers. And it's also true that when people optimize codes, they go back and remove unnecessary barriers. So it's like a race car driver with brakes. I mean, you don't want to use your brakes more than you need them, but you're not going to win a race without any brakes, right? So that's barriers. So don't let anybody act like a barrier is an inherent flaw in your algorithm or your thinking. No, there's tons of places where barriers are just required to make things work. Okay, you saw the way we stepped through synchronization. I took it from the perspective of PE0 and then the other PEs. I lumped them all together, and that's fine too, but you can in your head be like, I just picked up PE3. I went through PE0 and PE3, and I worked my way through the code to see how they're flowing. They're picking their way through the code. That's the way you want to think of your code. You want to work your way through the code as each one of the PEs. You do not want to sit there and go line by line like it's a serial code, because that will confuse you. Instead, realize it's copies of a serial code, and pick PE0 and just go, PE0 is just a normal process running serial code, and here's the way it picks its way through it. And MPI is just these funny communication and synchronization routines that are in part of the serial code. So, okay, now that we've got the actual basic pieces we can build anything with, let's go and do something that's actually interesting and useful in parallel. And we'll start to also expand our library of routines that we have available. And we'll see, we could do things with the handful of routines we have, but we'll find it's nice in life to have some of these other routines to make life easier. So let's pick an example of a good problem to do it. We're going to do an integration routine. And integration is a huge part of a lot of scientific problems. And the way we're going to do this particular integration, it might be a simple integral, but it's very, very scalable and would work just fine on much more complex, highly dimensional integrals like you come across in many areas of scientific computing. And the way we're going to do this is we're going to start with the basic way you learn to do integrals back in high school is you take a curve and you take the area under the curve and you approximate it with a bunch of rectangles, right? It's standard Simpson's method or whatever it's called for finding an integral. And that's numerically what we're going to do right here. We're going to take our curve, it's going to be a circle, and we're going to find the area under it. And by the way, since it's a circle and we find the area under it, it's going to be a way of approximating pi. So we're going to approximate the value of pi by finding the area of a circle. And the way we're going to do this in parallel is if we wrote a serial algorithm to do this, it would just go and divide the circle up into all these rectangles. And that would be fine and that would work. But we can do it in parallel on, say, 5 PEs. We could have the circle divided up into the same 10 strips, but now each PE only has to do 2 of the strips. So it's going to work 5 times faster. So by having each PE work on a subset of the strips, we can parallelize this very scalably and come up with our integral much faster. And that's exactly what we're going to do. So this is our example. Now we're going to take the opportunity here to introduce a few more commands, some very, very useful and common ones that we could do without technically, but we wouldn't want to. And first one we're going to introduce is broadcast. And broadcast is a command to, as it suggests, allow one PE to broadcast a value to all the other PEs. We did that in our last example. We had PE0 wanted to send this number 4 to the other PEs. And we did it with a for loop. And that's fine, that works. But it's, first of all, a little bit messy because you want to do this a lot. So wouldn't it be nice if there were a single command that allows us to broadcast a value? And indeed, MPI gives us this MPI beatcast command. Also, isn't it a lot more efficient? And the answer is yes. It's like me giving this lecture. I could do it point to point with each one of you with a single, point to point Zoom session. I could do it hundreds of times, or we broadcast it. So broadcast is also more efficient. So MPI broadcast is something we're going to use a whole lot. There's also something that we've seen the principle of before, reduce. which we actually kind of hid in our last example, which is where we had PE0 collect the sum from the other PEs at the end of that exercise, right? It collected this number from the other three PEs and added it together. That's a reduce operation, right? Similar to exactly the same as what we did with reduces in OpenMP and OpenACC. We said we have private variables that each have a subtotal, and we want to reduce them down to collect them together. And I said reduce is going to show up again in MPI, and here it is. And it showed up in our last example. We did a reduce, we just did it by hand. We had all three of the PEs take their subtotal, the numbers 4, 8, and 12, and send it to PE0 to add them together, to do a sum reduce. Well, that happens a lot in coding. So wouldn't it be nice if there was a command to do it? The answer is yes. Wouldn't it also be more efficient? And the answer is much more, because a reduce operation can be done in a folded way. And it's important to understand how much more efficient this is. So you use reduces when you can. If we had everybody in the audience out here had a number, and I wanted to sum all your individual numbers together. Well, let's say we're back in a classroom. We're back in a wide area classroom. We're all in a classroom, a lecture hall, and everybody in my lecture hall has a number. So we got 260 people or 50 people in the lecture hall, and they all have a number, and we want to add them together. Now they could each stand up, tell me their number, and I could add it on the board, and it would take 250 cycles to add those numbers together. Or I could say, everybody turn to your neighbor and add your number together. Now in one step, boom, we're down to 125 numbers. And now I could say, everybody with a total, a subtotal, turn to somebody else with a subtotal and add your numbers together. Boom, now we're down to 64 numbers, right? So we easily fold down the number of numbers to from 250 down to our final total in 8 steps instead of 250. So this idea that reduce operations can happen concurrently in parallel is a huge efficiency gain. And indeed, that's what MPI does for us behind the scenes. So just by us using MPI reduce, it saves us typing a couple lines of code, making some for loop to do it, but it also is much more efficient. So that's MPI reduce, and we're going to use it here to take our subtotal sums of our integral and reduce them down together. Now, broadcast and reduce all are what are called collective operations. So is barrier. It means they require all the PEs to participate. So even though only one PE gets the answer, gets the reduced value, or one PE gets the broadcast, all the PEs call the same reduce or the same broadcast routine. And that's why it's called the collective. Okay, so here's our finding pi code. By the way, I want to introduce one more thing in here that's really simple and common, and that's MPI com size. I said we like codes that are flexible to run any number of PEs. Well, so far, for the sake of simplicity, our examples were all kind of hardwired to run on 2 or 4 PEs. Well, let's make our pi code a little bit nicer, since it's starting to look like a real code. Our pi code will run on any number of PEs it started on. So the user gets to pick at runtime. When they type MPI Run, they can say, I got 100 PEs I'd want to work on this integral. So they can start on 100 PEs. So they can say, it's my laptop. I only have really 4 cores. I'm going to start it on 4 PEs on my laptop. And so it's nice if the code can be flexible. And real MPI codes are flexible. And so com size is an MPI routine that you can call to say, how many PEs do we have amongst all of us? How many of us are there? And so in addition to just finding out that I'm PE number, say 3, I can find out I'm PE number 3 out of 100 PEs. So there are 100 of us out there, and I'm PE number 3. And that can help me figure out where I should fit in this scheme right here. So com size tells us, in this case, we'd say there are 5 of us. And the rank tells me that I'm number 3. So I know what slices to work on. So com size is pretty common in MPI codes because it allows you to figure out how many PEs where you fit in the big scheme of PEs. So that's the last MPI call. So here's our MPI routine to find pi. And we can step through it here. Calls, has a header file, init, com size to find out how many PEs there are, to divide the slices up into, com rank to figure out which PE. PE0 is going to ask the user how many intervals they want to divide the slice up into. So the user might type 1,000,000 or might type 10 million, depending on how accurate they want their approximation to be. And so the user gets to decide at runtime how many slices. And we only want one PE to ask the user that, right? We don't want all the PEs asking the user that. So PE0 asks the user how many intervals, and then PE0 is the only one that knows the answer, so it best send it to the other PEs. As I said, we could use a for loop to do that, but now we have this broadcast command in hand. And so all the PEs call broadcast. It's a collective operation. Now, this is one thing that throws people off a little bit because the name of broadcast, the nomenclature, is a tiny bit unfortunate. It's called broadcast, and so it sounds like PE0 here is the one broadcasting. That's great. The other PEs also call it, even though they're receiving. So just beware that the collectives are named, for the operation, even though some of them are receiving and not broadcasting. So it's a collective. All the PEs have to call broadcast, even though most of them are on the receiving end and only one of them gets the broadcast. Which one gets the broadcast? Well, it will usually be PE0 because it's the manager, but in reality, it could be any PE. So this parameter right here says which PE gets to broadcast the data. It's very often PE0, but any one of them could be allowed to broadcast it. All the ones that aren't 0, when they call broadcast, receive the data. So here are the arguments to it. This is the value that's being broadcast. We have to tell it to type. It's one integer. PE0 gets to do the broadcasting, and we're not using any weird subsets, so it's the world communicator. So this is broadcast. We have the number n. It's going to be an output variable from PE0 gets to broadcast it. The other PEs, when we're done, are all going to receive this into this variable n. It's one integer, and that's all there is to it. So after broadcast is called, they all have the same value for n. So they all participate in broadcast, but only this PE0, gets to be the one sending it. The rest of them receive. Then we got our math going on here. So this is just the math of dividing up our circle into a bunch of slices and having each PE be responsible for the correct slices, the right start and end for its slices. So nothing profound here. This does all the integration. And when we're done, each one of the PEs has this subtotal for its slice, and we need to combine them all together. And that's what this reduce operation does right here. It says, I want to add them all together. So these are the parameters here, is we have, it's a collective. All of them call reduce. Here is the individual sums, partial sums, my pi, I would call it here, the partial sums of pi that are being reduced. Here is the final total sum that they get reduced to. This is the type. It happens to be one floating point value, so we're combining a bunch of floating point values. This is the type of reduce operation because we have different reduce operations, right? So far, we've seen sum and minimum and maximum. In this case, we care about sum. MPI has a bunch more predefined ones. And in MPI, you can actually even define your own reduce operations if you want. But most of the time, you'll be perfectly happy with sum and min and max. And so we're using sum right here. So we're going to sum all of these together. And this is the PE that gets the final result. By default, reduce operations go to one PE. And so PE0 is going to get the final result. There is an all reduce where all the PEs get the result, but we don't need that here. We're going to use the regular reduce. All the PEs get this reduced value here. P0 gets the reduced value from all the PEs. And again, we're using the regular world communicator. So this is the reduce operation. Now PE0 at this point in time has this reduced value, and it can print out the value of its found for approximation of pi and compare it to a more precise value to see how far off it is. So this is a nice code. It does real work. It's reflective of doing an actual parallel integration, which is a very important operation to be able to do in lots and lots of codes. And you can see how we rolled in a few more very common MPI routines that we could have done by hand with for loops, but it's more efficient and it's also cleaner code to use the MPI routines. So now you've got the real core set of MPI routines that are very, very useful. Okay, we'll defer this MPI when not to use MPI routine for the outro talk because we're going to go over this later. But instead, because of time, we'll just jump into our exercises. Now, before we do the exercises, I mentioned it's important to have very, very useful, I should say, to have the MPI docs, one version or another of the MPI parameters and commands available to you. So in your browser, you should have something. If you go to the MPI forum, there's a lot of different documents available there. And so you might find one in particular that you love the way it's organization. Here's one I find useful because it's a nice index. Just click on the MPI command and pull up the parameters. But there are lots of MPI community is huge and mature, lots of different options. And by the way, people usually ask, are there books? Are there good books, or more permanent references on this? And there are. There are a couple of fantastic books written by people that are heavily involved with the MPI committee and have been for a long time. And so if you really want a book on it, I can suggest both of these. The beginner one and the more advanced one are two good books. But the most important thing for you right now is to have some nice browser page open to you because you're going to do the exercises. And our first exercise here, a couple of exercises. First one is to write a code that runs on 8 PEs and does a circular shift. In other words, it shifts the data around from PE1 sends data to PE2, PE2 sends to PE3, and the one that's on the top, PE7, should send it a wraparound. That's why it's a circular shift back to PE0. Or you could shift the data down if you want. You could have PE0 send to PE7 and PE7 send to PE6, whichever one you want. But send some data in a circular shift. And do get this exercise working because this is an important one to make sure that you understand the basics of MPI and compiling and getting everything just plain running. And we don't want to move on to our Laplace exercise, for example, without you being able to do this. So get this exercise working. We have plenty of time for it. We're not going to use our upcoming break for it. We have more time beyond our break. So this is an important one to get working. The exercise 2 is a little trickier than it seems. And so this one, you don't have to worry about finishing so much in the time allotted, but you might want to at the very least give it a shot or think about it. Exercise 2, we want to write using just the basic send, receive, and barrier commands. We want to write something that substitutes for MPI com size. In other words, figures out how many PEs it's running on. So if I started on 4 PEs, it'll know it's running on 4 PEs. If I start on 16 PEs, it'll know it's running on 16 PEs. Now, as I said, that's what MPI com size does that we just used in our pi example. And so this is what you'd always use in a real code. But let's see if you can reproduce com size with just send, receive, and barrier. And I will tell you right now that it is trickier than you probably think it is. It is quite tricky, trick being the key word here. So it is difficult. So don't kill yourself on this one, but think about it. But please do make sure that in our exercise time we have, you can do this one. And we'll give ourselves, I think we have 45 minutes allotted to this exercise, which is not starting now. This is our break starting now. Feel free to do the exercises if you want to over the break. But when we come back from the break at the top of the hour, an hour from now, we'll have dedicated time to sit here, answer questions, and deal with this. And again, please give exercise 1 your full attention. Make sure you can do this. Exercise 2 is a little more optional. But we'll take 45 minutes for that starting at the top of the next hour. Now I'm going to disappear. So there's a summary of our exercises here. I'm going to disappear somewhat over the lunch break, do the Zoom reboot thing again because we find it useful in keeping Zoom alive, which means if you type chat questions, well, I'm not online. I never see them when I come back. Chat gets purged. So I'll answer all the pending questions right now and I'll hang around until they're all answered. But those of you that are heading off to the break can do so now. Come back from the break at the top of the next hour, work on exercises, and we'll be here to answer your questions as you work on exercises. Okay, but you can disappear now if you'd like. So I'm going to go pick off the last couple of questions. Doesn't look like there's a ton here before we start on our break. Okay, bear, wait until all the P's are finished. Let's answer that. Possibility the P's start going. It's possible. So other P's start going computations before broadcast the information to them. I'm assuming you're talking about the pi code here. So is it possible for the other PEs to get, that's actually not a bad question in the sense that one thing I didn't emphasize a whole lot was that MPI broadcast is a blocking command as well. It blocks. So when you do a broadcast, all the PEs wait until they get the answer. So none of them can get past this broadcast. It is an implicit barrier is another way to say it. It's got an implicit barrier because all the PEs have to get their answer before they can continue. And so PE0, for example, here has the answer. Other PEs can't jump ahead down here and start computing before they get the correct value to use for N because they have to receive from broadcast that correct value of N. So broadcast and reduce as well are blocking. The PEs aren't allowed to continue through it until they've got what they need for an answer. Shouldn't we use a barrier before the broadcast to make sure the number of intervals is in PE0? No, because relating to what I just said, and I may have answered it for you, but I'll answer it a different way, is that the other PEs are going to jump right past. So the other PEs jump right past this PE0 thing, go right to the broadcast. And they're waiting here on broadcast for PE0 to finally get there. So they will typically just jump. Again, I don't want to make any assumptions about what's slow or fast, but on average, we're going to say the PEs come down here and jump right to the broadcast while PE0 is up here waiting for the user to input the value. And they're stuck here because this is blocking. So they'll be waiting for the user here. Finally, when the user enters the value and PE0 gets down here and is able to broadcast it, that's as soon as they can receive that value and continue on their way. So reduce is the same as broadcast and all PEs call it. Yes, indeed. Reduced and broadcast are called collective operations because all the PEs have to collectively participate in it. So all the PEs will collectively participate. If you want to change that behavior, that's where we get into communicators. So later on, we'll talk about communicators, how you can get fancy. But by default, when you're using MPI Com World, everybody participates in any collective thing, which so far our collectives we have are broadcast and reduce and barrier. Do we run this on login node? No, you do not. You grab an interactive node. with PEs to do. Did I have that in the? Yes. So here you grab an interactive node before you can run this stuff. You compile with MPI CC or MPI F90, and then you run with MPI Run. So this is the process right here once you've edited the code. Okay, with that, it looks like I've caught up with questions. So I'm going to do my reboot thing here, which means please, again, do not submit chat questions until you see me back online, because I won't know that that happened. So we'll see you all back here at the top of the hour after the break to continue working on our exercises. Okay, we're going to get started again in a couple of minutes and review some exercise solutions, but I'll pick off the remaining questions here that just came in the last few minutes. Can we use MPI Send instead of specifying target send every node? Well, that's exactly what broadcast is. So no, MPI Send is strictly point-to-point, and broadcast is for exactly that, to send to every node. Let's see. And there are variations too. We'll talk tomorrow about using gathers and scatters, which also send things and collect things from multiple nodes at once, but send is point-to-point. Okay, Tom's been picking off things here technically as well. Let's see. For the first parameter to broadcast is the variable. So we'll get us. Oops, get my slide going here. If we look at our MPI code or our Finding Pi code here, this is the parameter that you want to broadcast from the broadcaster. It's also the parameter that gets received by all the receivers. So in this case here with our Finding Pi code, the P0 finds the number of intervals that the user wants to specify, and then in the process of broadcasting it to the other PEs, they also receive it. So for PE0, it's the value it's broadcasting, and for the other PEs, it's going to be set to that, equal to that value. So they all walk away from broadcast with the same value for N. I'm not sure exactly which one is solution 2C, but if you get an invalid rank, is MPI's way of telling you that the PE doesn't exist that you're sending to. So it means you're trying to send to PE6 on an MPI run that you only started with, say, 4 PEs. So it's an excessively high PE number. So make sure that you ran that code on the right number of PEs. You specify all PEs to send a message to certain PE. Does it send to itself? I don't know exactly what exact command are you referring to there. So things don't typically send to themselves because, for example, broadcast doesn't send to itself because it's broadcasting the value. So why would it? It's going to end up with the same value when it's done. So say, broadcast here says P0 has the value 5,000. Well, we start out broadcast, it's 5,000. When we're done, all the other PEs have 5,000 too. Well, but how to use the communicator and status values? Well, as I said, we haven't gotten into communicators yet. We're not using them for anything fancy. So the communicator should always just be calm world. Tomorrow, we'll talk about how we could break things up into subsets and work with various subsets of PEs and how we can define those. In that case, we'll get into how to use calm world. As far as the status variable on the receives, let's see, we don't have a receive here per se, but the status variable returns information about the message that you may or may not want to follow up on. And none of our examples so far has it been useful to. But if you receive, say, a message from any PE, so you might use, say MPI can receive a message from any PE. After you receive the message, you could use status to see which PE sent the message, where the source was. So if you look at status, it's a structure, and it's got source, it's got tag, it has error conditions, it has count. So it gives you details about message that was received that you can, if you care about those details after you receive the message. And so far we haven't used it for anything. Let's see. I'll have some examples tomorrow in advanced MPI stuff of receiving messages where you don't know their size in advance. So sometimes if somebody might send you a message and you don't know how big the array is, that's a possibility. And you can use status to see how big how big the message really is. Okay, with that, we are going to move on and look at some solutions. So consider this exercise session officially ended. We'll review some solutions, at least my solutions. Yours probably look kind of similar to what we've just been working on. And then we'll move on to a more substantial exercise, one we're familiar with, the Laplace code. Okay, well, one solution for the shifter, this is the C1, we'll look at a Fortran one solution for the shifter, and it's not the only one, so you may very well have done things differently, is something like this. So here we've got all the boilerplate code, the header file, init, com rank to find out which PE we are, finalize, so that's all generic. So the actual code here is, I want to circularly send data around. So if I'm PE number 7, I want to send the data to 0 because we don't want to send it to PE doesn't exist. Everybody else is just going to send the data to the next PE number up. So all the PEs just send it to their PE number plus 1, and they send this number to send, which up here I just set equal to whatever I set it equal to. Oh, here it is, to the PE number. So that makes it easy for me to make sure the right things are happening. So I send this number to the next PE up. I happen to use a tag of 10 because who cares? And then that means all the PEs should receive a message. And so they all receive a message, which is again the same one integer they sent. They're going to receive a message from anybody, tag of 10, and they print out what they received. So in my code, it'll print out PE6 will print out that it received a message from PE5, the message 5 from PE5. So this is a simple example. Again, yours probably looks somewhat similar to this. Here's the Fortran one doing exactly the same thing. And this is having it wrap around from PE7 back to PE0 as I'm sending up. If you're sending messages down, you probably have your message go from PE0 to PE7. So it is like that. Let's see. So much simpler than what you thought you needed to do. Yes, this stuff, the more you understand it and you think in terms of, you think in an MPI mindset, the simpler this stuff gets. It's hard not to overcomplicate things because you want to think there's some magic parallel stuff going on here, and there isn't. This is just a serial code running away with 7 of its buddies. So just 8 copies of this code running away, and they're just exchanging some data back and forth with the MPI commands. It is that simple. And yeah, and it's going to take some experience and some practice for you to get comfortable with that notion. But once you do, you'll find out that MPI is, yes, it can be quite elegant and quite compact to accomplish a whole lot. And tomorrow in the advanced MPI stuff, we'll see there are the more routines that you learn and roll in, a lot of them just make things even more compact and elegant as we go. But with what you know right now, though, you could do pretty much anything if you had to. But we'll learn routines to just make life even easier. Okay, so much for exercise 1. And this is the kind of output that I had for my particular thing. Just make sure each PE received a message from its neighbor and prints it out. Okay, that is exercise 1. Let's see invoke. Okay, question. Let's see, invoke 4 PEs encoded in a fashion of 3 PEs complete and 1 is stuck with the whole MPI execution not computed. Yes, so if one of the PEs gets stuck, the whole code tends, hangs there. So if one PE, it's a very common bug to have is when you're doing even this exercise. I am sure some people doing this exercise, one of the things that notified you that you had things slightly set up wrong was you ran it, it just hung because probably a blocking receive. A receive didn't get the right send, and so the thing sat there and hung. Control C to get out of it and and stare at it and fix it. And if we were on more complicated problems, we could use a debugger like we'll look at tomorrow to figure out exactly where it got stuck. But yes, a very common thing is your MPI code just hangs because some receive somewhere isn't working. And that's why people start to stick in some print statements to say, got here, and they go, oh, it gets stuck here on this particular send or receive because I accidentally didn't do it. Okay, so that's that. Exercise 1, you could, what if these messages were huge? I mentioned deadlocks earlier. What if these messages were not just an integer, but were huge data, were hundreds of megabytes or gigabytes in size? We could technically run into that deadlock thing we had earlier, the way we're doing it here, because we're having everybody send and then everybody receive. And if you recall before, if these messages are huge, and the definition of huge is very fuzzy. That's a thing that's important to remember. Huge depends on how big of a buffer you have on your sends and receives and MPI parameters that you can override. So you don't define how big something is before it starts blocking an MPI with an MPI send. It's a fuzzy line. And this code, if these things were more than an integer and we're sending huge messages, they could run into that deadlock problem. But we could fix it actually if we move the sends. So it sent, one of them sent before it started to receive. I don't want to belabor this point here, but I'll just show you if you want to actually go back and stare at these things right here. This code, for example, won't deadlock because PE number 7 is always trying to receive a message before it sends its first message. So even if everything's really huge and the sends would get stuck, this PE7 would save the day because it would start to receive the message from PE6 before it tries to send its message. So then PE6 would eventually send its message through and be free, and then PE5 would receive the message from PE5. So this would break the deadlock. But again, I'm introducing a problem we'd never see here with small messages. But if these were huge, that's where we run into the deadlock. So I just put that in there for people that want to think about the subtleties of things. But I would suggest you not concern yourself too much with that at the moment. On the other hand, exercise 2 is intended to introduce a little bit of humility if you think this stuff is, for those that think it's too easy and too straightforward. There is no possible solution for exercise 2. You really can't write a code that replaces what com size does and tells you how many PEs you're running on. As a PE looks around and tries to figure out how many neighbors it has, it can never be sure because there could always be some node very far out there that it's tried to ping, it's tried to connect to, that's there, but just hasn't gotten back yet because it's further away on the network or it's a slow connection or a very slow node. So this is good because, and the reason I told people not to spend a lot of time on it, because you can't solve the problem, but if you try to come up with a solution for it, and you think it works, and many people do, many say, I ran this and it worked, but ask yourself if one of the nodes was really, really slow or very, very far away. So what if your nodes were spread across the solar system and it took light minutes for the connections to happen between the different PEs? Would your algorithm still work? And if you're honest with yourself, the answer will be no. There's no algorithm that can't always be sure that there isn't some other PE that we haven't yet heard from as we're trying to somehow count the number of PEs. And so don't let this frighten you. This is not a problem you run into a lot. It's not hard to write MPI codes that are very robust and always work, but this is just an example of making assumptions about, the nodes all run at the same speed or the network's very fast. That is dangerous to do. Always ask yourself as you're writing your code, would my algorithm still work if the things were spread around the solar system or one PE was 1,000,000 times slower than another? So you notice those are the questions that I asked myself when we were doing our previous examples. I said, would this work if one PE was 1,000,000 times slower than all the rest, if it was really slow? And the answer should always be yes. The answer could be, yeah, it's going to really slow everybody down. We're going to have to wait for the slowpoke, but it should still eventually work. If you somehow are writing an algorithm where it depends upon all the PEs running at the same speed or whatever, you're writing unsafe, broken code. So there's an almost solution. Once in a while, somebody comes up that's really thinking out of the box, thinks about this one. As a matter of fact, somebody had a question about invalid ranks earlier, running one of the simpler examples. And you could try to write a code that writes the higher and higher PE numbers until it gets an invalid rank error. And that tells you how many PEs you have, right? So say the code PE0 in this case just tries to write the PE1 to PE2 to PE3. And eventually, if you run this on 8 PEs and it tries to write to PE number 8, right, which doesn't exist, that's going to be an error. And if you've been paying attention, close attention so far, you notice the MPI routines return error conditions. And so you might think that's a way to figure it out. You could check and see if MPI Send isn't successful. We could actually check the error condition. And this is so close to actually being a good solution. The only problem is by default in MPI, the error condition that it returns when you send to an invalid PE is just a runtime error that will crash the code. Instead of returning an error condition here, it will stop the code. It will assume something's really bad. That's the default behavior. And so if you tried a solution like this, you'll find that invalid rank error, which I'm sure many of you stumbled upon just in trying to get the shifter to work, is an invalid rank error. So that's, unfortunately, this won't work. But to show you how flexible and advanced MPI is, you can actually tell MPI to treat errors differently. So we could change this error behavior and say, instead of crashing here, actually stay alive and report this MPI success instead. And then this example would work. So we can change the error handling in MPI. But of course, we didn't get into this, and many of you will never care to deal with this particular little piece of MPI capability. But this is kind of a completely out of the box solution you could kind of make to work here. But any normal solution of I'm just going to send messages back and forth between PEs and somehow they figure out how many of us are hanging around will not work. So let me see. There are. It's possible to have an alternative where every node is broadcasting its own number to send, where each of them only receives from the node next to it. Broadcast and receives are two separate things. You can't use them at the same time. A broadcast, when you have a broadcast in your code, well, we don't broadcast anything here. A broadcast is a collective. They all call broadcast. So you can't have a broadcast and a send trying to kind of work together. They are not compatible. Broadcast, all the PEs call broadcast, and that's how one of them is actually broadcasting it, but the other one's calling broadcast or receiving the data via the broadcast. You don't call broadcast and have receives on the other end. So you can't really mix a broadcast and a receive kind of operations. Should there be an MPI receive command? I don't know exactly what you're referring to, since I've been whipping around my slides here since you asked that question. So there are MPI receives where there should be in all of these examples here. Unless you mean on this one here, which is to try to find things by an error, in which case, no, this is one of those rare cases you'll have a send without a receive, because we're trying to break things. We're trying to send to where it's not going to receive. We don't really care if it receives the message. So this is not really a very typical piece of code. So there's no receive here because this is a very weird piece of code. I can't argue with this comparison. Something from the very popular three-body problem. Let's see. Solution, sending data to PEs, not receiving data will freeze the code at some point. Sending data to PEs that don't exist will actually cause this invalid rank error to happen when the PEs don't exist. Yeah, this solution here happens to only check up to 512 PEs right here, but you could change this number to anything you want. I just assumed this was during the workshop. You know, people aren't usually running on more than 32 PEs or something like that. Yeah, this solution doesn't check bigger than 512. You are correct. This is kind of assuming on it. How does MPI com size work? MPI com size works because it knows when it starts things. It knows what you type to MPI run. So it's cheating. MPI com size is a total cheat. It's part of the system that's setting everything up and assigning the PE numbers and everything else. So it has inside information. It's not trying to figure it out from scratch. Okay. Well, I am happy to answer questions about these exercises and everything from the, all the materials we've done so far on an ongoing basis. So please don't hesitate to, to dig back into these materials and ask questions as we go. But I will move forward right now to our exercise that we're going to do, which on one hand is familiar, but on the other hand is going to cause us to address this problem in a very, very different way than anything we've done so far. And so it is our Laplace exercise. So we don't really have to go into great detail and explain the exercise because we're all familiar with it at this point in time. And I hope you are starting to believe that, that our capabilities, the things we've done so far and you're going to do, we're not gimmicked by me picking a super easy problem for GPUs or a super easy problem for CPUs, or here a super easy problem for MPI. Because you can see we've been trying all these different techniques on it. But we're going to do it with MPI here and find out that it's a little bit harder in some sense. Now, the payoff in the end, as you put this extra effort in, you go, wow, this is so much easier with throwing a few directives at some loops with OpenMP and OpenACC. The extra effort you put in here is because this will now scale up to run on 1 million cores. The solution that's, that I have, and probably most of you will come up with something, it should scale up and run as large as you want because it'll run across nodes. That is not true for our OpenACC and our OpenMP solutions, right? They only run on a single node. That single node might have, 128 cores, so it can speed up a whole lot. It might have some GPUs in it and speed things up by 30 or 40 times, but none of those can speed up 10,000 times or 1 million times or work on a problem that's much, much bigger and takes up more than, a couple 100 GB of memory. The techniques we're using with MPI here and the solution you'll have here will scale up to run on terabytes, petabytes of memory if you want to scale the problem up. Okay, so once again, our Laplace code kernel is, I hope at this point in time, we're all kind of familiar with it. The loop just is going to keep running until it converges on a solution here or until it runs out of iterations as we allow it. So I won't belabor explaining this, although I'm happy to go back and answer questions, but I'll assume for everybody's sake, we're all kind of comfortable with it at this point. The difference here is going to be these subroutines before, which I just mentioned kind of in passing. I said, these initialization routines and the print routine that we have here, I just point out they exist and they do their thing, and it's not that interesting because we had the luxury of focusing on the kernel of the code right here, the central part of the code where all the number crunching is going on. We're going to find out that that is not quite true anymore. Now we are going to have to go everywhere in our code where these data structures, temperature and temperature last, exist and make sure that they're compatible with the way we're going to do things with MPI. So now we're going to have to go back and dig into some of these subroutines. So it's not that incremental loop at a time approach we could do with directives. It's going to be a more involved approach. And this is the reason why MPI ports take more effort. Again, huge payoff, infinite scalability, but you're going to see more effort. So Fortran code, again, we won't step through it because by now we're all familiar with it and what it does, but we are going to find ourselves digging into these subroutines a little bit as we turn this into an MPI code. And the reason for this is that the thing you do with MPI that's different from any other of the approaches we've tried is we have to break our problem up into pieces that live in different processes on different pieces of hardware. Before, everything we worked with had a shared space in memory. It was either just a shared memory of the cores, or even with GPUs where we moved data back and forth. When it was on the GPU, all the cores on the GPU shared it. And when it was on the CPU, they all shared that space. Now we're breaking our problem up into a bunch of little fundamentally different pieces. If it were our weather code, for example, each one of the processes might own a different state of the map. So they're fundamentally broken up. They're different chunks of memory. The original full map no longer exists anymore, except in our heads and on paper. That's what we're going to do with the Laplace code. Our metal plate is going to get broken up into, we're going to start with 4 pieces. So we, although our MPI code should be flexible and be able to deal with however many slices, to keep life simple and have a concrete example, we're going to break our metal plate up into 4 pieces. And so our 4 pieces that we break our plate up into could be different. They could be these squares like we're doing here, or they could be slices or whatever. Now, one thing, and this whole step of breaking your problem up into pieces is called domain decomposition. That's the term you'll hear. And it's the most important thing when you're parallelizing a code with MPI is to get this right. If you get this right, the code more or less kind of writes itself. It's pretty obvious where you need to put the message passing in and what kind of data you pass around. If you get this wrong, you probably have doomed your project. You might spend time putting in MPI to do things here and there. And when you're done, the code doesn't scale and run well. And it's not a trivial thing to fix at that point. This is the foundation on which you're going to build your MPI port. So how could it go wrong? Well, this domain decomposition I've got in front of us right here would be a very dumb one, but one that people tend to, beginners sometimes do as their approach, which is to take our 1000 by 1000 plate and make 4 copies of it on each one of our 4 PEs. So again, we're going to assume we're just running on 4 PEs here. So we're running this on 4 PEs. So each one of the PEs gets the whole 1000 by 1000 temperature and temperature last array. And then they're just going to work on 1/4 of the array. And that might seem like a perfectly reasonable thing to do. We don't have to change much of the code. We just have each PE only, work on a section of the array. Because it's the kind of thing we did when we had shared memory machine. We just said each one of the PEs works on some strip of the array. So maybe that's a place to start with MPI as well. Copy the whole array around. And this is wrong. Anytime you find yourself with an MPI port copying your big data structures around globally, the whole data structures, you're starting down that bad path. It's going to be disastrous in the end and maybe painful if you spend a lot of time trying to do this. So you never want to copy your whole data structure around. That's not the way to go. Instead, we want to break it up and have each one of the PEs end up with just a small piece, not the whole thing and only work on a small piece. And there are multiple reasons for this. The main reason, well, one of the main reasons is that if you do this, your code is never going to scale up a whole lot in the sense that one of the reasons you make an MPI code is so that you can attack bigger problems. Let's say that one of the problems we have is that our plate isn't a high enough resolution. right? Very often in scientific code, that's exactly one of the reasons you're scaling up and running on supercomputers. We don't want 1,000 by 1,000 metal plate. We want to have a million by million metal plate. And a million by million metal plate isn't going to fit into memory on any one of these nodes. So that's the whole reason we go to MPI. Is with MPI, we can now run that million by million metal plate on 1,000 or 10,000 nodes. And now it will fit, the little pieces will each fit on one of the nodes. But if we try to keep the whole million by million plate and copy it to all of the nodes, it'll never fit. So to make things scale, you want to make sure that as you break your problem up and split it up, that the pieces get smaller. They don't stay the same size and you work on a smaller section of them. So that's one of the reasons. The other reasons are we'll have large messages to pass around. There's all kinds of reasons why it's bad, but we'll stick with that reason as the main one right now. So at any point, if you find yourself copying big data structures around instead of breaking them up into small pieces, you are doing a bad domain decomposition. So let's instead break our problem up into small pieces. So we take our original 1,000 by 1,000 Laplace array, that's our metal plate in our Laplace problem. And now we break it up into these 4 small squares. And no longer anywhere does it really exist 1,000 by 1,000 array. Instead, each one of our PEs now has a 500 by 500 array. And there are 4 of them. So back together, if we put them all back together on paper, we have our 1,000 by 1,000 array. But if we look at the code now, the code only has 500 by 500 arrays in it. This is a good domain decomposition. As we go to larger PEs, we break our data structure up into smaller pieces. There will no longer be 1,000 by 1,000 array anywhere in our code. So it really exists as our problem. Our problem is still 1,000 by 1,000 metal plate, but no longer does that physically exist. This is a good domain decomposition. So this is the kind of thing we want to do. And it'll improve lots of other things too. Besides being scalable, the communications are less, and everything's better when you do it this way, when you break things up into pieces. So we go into our code, but everywhere we had that original temperature and temperature last array defined as 1,000 by 1,000 array, we need to go back and break it up into smaller pieces. And that's why we have to go through our entire code and not do this incremental approach where we can just go and look at one loop at a time. So this is a good approach, and there's no reason not to use this. As a matter of fact, this would be, if somebody said this is what I'm gonna do, it'll be good for you. But we're gonna, to make life even a little bit simpler for you, because this approach, again, it's fine. And the problem is, it's not a problem. It's just, it's a slightly more complicated, and we're sending messages of rows and columns of data. And so that's a little bit trickier than what we're gonna do. So I'm gonna suggest that we instead, for our approach, go with breaking things up into strips like this. And this way, when we send messages, they're always just all rows of data. They're not rows and columns of data. So it's gonna be a little bit easier. Also, this scales a little bit easier. What if we decide we wanna run on 5 PEs? Well, we could just break our metal plate up into strips that are 1,000 by 200. How do we break the squares up into 5 pieces? A little trick. So we're gonna go with this. Nothing wrong with squares, but we're gonna go with this approach right here. So we're gonna do our domain decomposition by breaking up our metal plate into strips like this, each one of which is going to be in a separate PE. And it's going to be, each PE then is only responsible for a 1,000 by 250 metal strip that it's responsible for calculating. And so this is a very common kind of way to decompose things. It's just break it up into chunks. In the real world, where problems are mostly 3D, we can imagine these would be slabs or cubes or something like that. Or actually, in even the more real world, where things are often finite element meshes that are irregular because our shape isn't a square metal plate, it's a turbine blade that we're trying to thermodynamically model. And it's got a twisted fan propeller shape. And so it's a finite element mesh. And so breaking that up, the chunks get much less regular, but that's where, you know, most codes are these days. And MPI is fine in dealing with that, but we're just getting off the ground here. So we're going to stick with our square metal plate, and we're going to break it up into strips like this. Let me see here. Okay, these are mostly answering questions about our last exercise. I'll quickly pick them off. I don't want to completely jump the track here. Let's see. What about a broadcast of the ranks and then reduce with the max? Well, we didn't allow ourselves to do this problem with reduce or broadcast. So if we could use other routines, there are other ways to solve this to solve our last exercise. I'm talking about our last exercise now. We're jumping back. We didn't allow ourselves broadcast or reduce, but yes, we could solve the problem with those, but not with sends and receives and barriers. There's a reason for normal solution upper bound the number. No, I just picked 512 because why not? There ought to be a number in there. Change it to 1 billion if you want, then it will work just fine. How do we know the number of P's we're running the MPI run -n command? Well, you're setting it as the user, you're filling in n, and then as the program, you're finding it out by column size. Okay, so now we're finally up to our example here. In this example, wouldn't it make more sense to break it into 501 by 501, then update to 500? Then each P is only responsible for its neighborhood and needs communication between P's and strips or ghost strips. Okay, well, it looks like you're just a couple slides ahead of me there. So you're asking questions that we're about to answer. Okay, so this is our domain decomposition right here that we're going to go with these strips. And because this is such a very, very common thing to do, just break up your problem into pieces and then communicate data between them, because these aren't completely independent problems, right? Because we broke the metal plate into 4 strips doesn't mean we have 4 completely independent problems living on their own island. The temperature, as it, the hot corner here is going to heat things up. It's going to have an effect up here. So the neighbors affect each other, right? Our Laplace iteration as it goes through and averages neighbors means neighbors that are on the border here do need to find out the value for their neighbor down below or up above. So the plates affect each other. We don't just have 4 completely independent problems right here. We now have 4 pieces of the problem, but they still need to communicate along the edges. And this is extremely common kind of pattern to have. And so there's a technique for it to break this up, which is called usually using halo zones or ghost zones and ghost cells, which we're going to use right now. And the idea is that we broke our metal plate up like this. And now if we look on each one of the PEs, we have this strip that's 250 by 1,000 long. And when we try to run the problem, we're going to need some information. PE0, for example, has the top strip. It's going to need at some point in its calculation, when it's calculating row 250 here, it needs to know the value, the temperatures in row 251, numbering on our, going back on our paper scheme, our global numbering scheme. It needs to know about row 251, which as far as PE1 is concerned is actually just row 1. Counting from 0. So PE1, when it's calculating row 1 up to the north, it needs some information to calculate its value from row 250 of PE0. So there does need to be an exchange of information right here. So these 2 PEs need to exchange some rows of data. And we'll find that if we just make sure we pad out each PE with this extra row to contain its neighbor, so these are the ghost cells, then we're not responsible for calculating these values, our neighbor is, but this gives us a place to put our neighbors' calculated values for ourselves so that our loop can just chug away and calculate. So the row 250, when it's calculating and peaks down at row 251, there is a row 251. PE0 is not going to update row 251, but it is going to look at row 251 to help calculate the new average for row 250. And so this scheme is, again, very, very standard where we've got these bordering regions where we exchange some information. And this is where you're going to spend most of your effort actually on this exercise, or indeed writing any MPI code where you've got a domain decomposition like this, is you just got to make sure you get all the math right, the indices right. That's right, welcome to programming, right? We just got to make sure our indices are right. So we got to make sure that our numbering is right. So if we're on PE0, we have rows that go from 1 to 250. This top row, the 0 row up here is actually the heating element, right? It's the boundary condition up here. So this is the boundary condition. Then we have 250 rows of data, our metal plate, and then we have a ghost row at the end, which is really our neighbor's data that we copy over every iteration before we use it. And that's fine and simple and straightforward. We just need to make sure that we also send our row 250 to our neighbor every time step so that our neighbor can use it for its row 0, right? PE1 needs to know about row 250. So every time step, we send row 250 down to our neighbor's row 0, and our neighbor sends us up row 1 up to our row 251. And by doing this exchange, we've kind of glued our metal plate back together where it matters, right on the edges. And so this technique, again, is very common, and you'll hear it called ghost cells or halo cells, halo zones. Those are the 2 terms you'll most often hear. And we're going to apply it to our Laplace code. Let's see. Questions here. We have 7 PEs, 1 up 7. So yeah, if we'll start dividing up our plate into odd numbers and everything else, we got to start worrying about math. We might have an odd size plate or whatever. We're not going to deal with those details right here, but it's just bookkeeping. So I hope everybody can see that it's just bookkeeping. If we wanted to break this up into 7, and we'd have to, now we're dividing 1,000 by 7. There's going to be one of the plates is going to be an odd size, and there's nothing terribly wrong about that. It just means we got a little more logic in our code. Or some packages, you'll notice some packages, for example, that you'll run will say your problem size has to be a power of 2 or something like that. That's their way of dealing with these mathematical issues. So we could write this code and say your plate size must be a multiple of 4 if we wanted to. That's the cheap way out. Or instead we have some logic and we say, okay, one of the plates is going to be, if we divide by 7, one of the plates is going to have a couple extra elements to it. So it's all bookkeeping. There's nothing fundamentally difficult to do. We're just not going to involve ourselves in that extra awkwardness. Okay, let's see. And but if we do have, so somebody raises a question, what if the node, if we do have PE3 has an extra couple of rows, it's going to be slightly slower. And that would be what we call a load imbalance. It has a little more work to do. So it's going to imbalance things. Other Ps are going to have to wait a little bit. And that's exactly true. And that is why in the real cases, and we'll talk about this more when we get into more, well, more advanced stuff here. In real cases, where this is a finite element mesh and the pieces we break it up to are very weird, irregular shaped lumps, the load balancing is never going to be perfect, but we spend a lot of our time trying to get it as close to good as possible, but the shapes are weird. So these are all problems we'll talk about, but we don't want to deal with right now where we're just trying to get the Laplace code to work, but none of them are anything more than fancier, more painful bookkeeping, which again, hey, welcome to programming, right? For overlapping regions, for neighbors, you follow the same process. So I'm not sure I understand your question. For overlapping, I mean, so if we had more neighbors, if this were 2-dimensional, for example, if we had neighbors over here, we'd have the same thing. We'd have ghost zones going off in this direction, or going back to like this. This problem right here is just fine. We just have ghost zones here along both edges like this. So as long as we have a ghost zone with our neighbors, we can pick any shapes we want, and these neighbors can even start to have weird shapes. As long as the overlap is along the edge, allows us to calculate when we're doing our own zone, as long as we have the information we need about our neighboring point so that we can continue to do our calculation, and we're good. And so, as I said, we'll look at some cases. I'll show you some visualizations where these get to be very irregular in the real world, where thermodynamic modeling in the real world is interesting as a turbine blade or the heat exchanger inside of your laptop. Those all have weird shapes. And so we're not dealing with regular shapes. And MPI is exceptionally good at dealing with weird shapes. As a matter of fact, later on, when we'll talk about why MPI is the only alternative to use on these kind of problems, why these other things, like somebody mentioned Chapel or X10 and other things, why they haven't gained traction. It's because dealing with awkward shapes is where MPI excels for reasons we'll get into. Whereas other approaches to programming, sometimes they look great for simple problems like the Laplace code, like data parallel programming. We'll look at data parallel, we'll compare it to MPI. Data parallel looks fantastic at working on problems like this. I'll show you how we could do the Laplace code, a couple lines of data parallel code. Problem is, when things get irregular, which is what you really care about, most of those approaches stumble very, very badly. MPI is fantastic at dealing with all these weird things, which you're already asking questions about. And believe me, the more you get involved with real problems, the more things you don't even anticipate come in, and the more irregular the shapes get, the more load balancing becomes a problem. In the real world of weather problems, things have very irregular shapes. Hurricanes don't just sit in one spot, they move across your map. And so you want to redistribute where all the work and the mesh is going. MPI is fantastic with that. Matter of fact, it's the only solution that's really found to work in general. But we're not going to clutter up our Laplace intro example to you as programmers who just learned some MPI 2 hours ago. We're not going to jump into all of that just yet. Tomorrow in the advanced talk, we'll look at how we address those problems. Okay, as a matter of fact, you don't even actually know how to even send a row of data right now, because we haven't really talked about it. What if we want to send a row of data, more than one integer? So far, all we've done is send one integer or one floating point number. How do we actually send an entire row of data? Well, that is a very easy extension of what we've been doing, because we've been so far, everything we've sent, our count has only been 1 in our send parameters and our receive parameters. They've only been sending one float or one integer. Now we find out why there is that count, because we can send an entire row by pointing it at the beginning of the row and saying send 1,000 of these. And that's exactly what we're going to do. We're going to just point it at the beginning of the row of data we want to send and send 1,000. This does introduce one minor complication here, and that is that Fortran and C actually go across arrays in a different order. One goes across in rows and one goes across in columns. What do I mean by that? Let me show you this right here. So if this is our array that we're trying to send data in C, if we want to send this strip of data right here, we point it at, so here's our array, an 8 by 12 array. In C, we point at element 3, 1, and that's going to be down here. It's going to go down here 4 and out 2, counting from 0. It's going to go down to here, and then we can say we want to send 4 of these. 4 of these integers, and it'll send these 4 right here. So that's the chunk of data that will be sent in our message. Okay, all well and good. Only thing is Fortran, for historical reasons, which have come to be a pain in the butt for everybody over the years, Fortran has the exact opposite convention, being more mathematically oriented. So it decides that it's going to go column major. So it starts 3-1 in Fortran, means it goes, well, first of all, Fortran by default will count from 1. So we're going to define it from 0 to 7 just to keep us on the same page here. So 3-1 in Fortran is going here. It's going to start here and go this way in memory. Fortran scans across memory this way, C scans across memory this way, and we want to send things that are contiguous. So this is what we want to send. Now tomorrow we'll find out how it's very, very easy in MPI to send. If you're in C, you could still send a column of data very, very easily, or in Fortran send a row of data. Matter of fact, we'll see how we could send a diagonal of data. So MPI makes it very easy to send whatever you want, but we don't want to jump into all that right now. So instead, to keep things simple for this exercise, we want to just make sure we're sending contiguous strips of data. And that's fine. All it means is that in Fortran, instead of breaking our problem up into rows like this, we're going to break it up into columns like this. That's the only difference. So the Fortran and C examples are just going to break up into rows and columns instead. And so this is this. Now, by the way, if this is news to you that arrays are laid out contiguous in one direction and not in the other direction, you should be aware of this because it's very important for performance in general, even in serial code. So in C, for example, if you write a loop, there's a reason why you want to change the last index in order in the innermost loop so that you go through memory, sending things one after the other in the array, because instead, if you start going this way in memory, you're skipping in our Laplace code 1,000 elements at a time through memory, and it makes it a lot harder for the hardware. It's jumping all over memory trying to gather your data. So in C, you'll find your loops, your for loops, I think is what I have right here. In C, you'll find whenever you write nested loops like this, like we've been using in the Laplace code, you always want to make sure that the innermost loop is the rightmost index. And that's what we've been doing in our Laplace code. Whereas if you look at our Fortran code, the innermost loop, J here is, I here is the leftmost index. And if we were to change those, you'd find the code would run, just the serial code would run a lot slower because this one goes efficiently through memory in C and this one goes efficiently through memory in Fortran. So those are things to be aware of if you actually care about having your code run efficiently at all, is be aware of whatever your computer language is, whether it's row major or column major. That's the term that you'll usually see in the documentation or the compiler. That tells you which index should be leftmost or rightmost when you're doing nested loops. So anyway, in our case, it's easy for us to deal with this. So in C, we're just going to make sure we're sending rows up and down like this. And so you might have a piece of code that looks like this. You might say, if I'm not PE0, I want to send a chunk of data up to my neighbor. So you might say up is equal to my PE number 1, and you'll say send. Point this at the beginning of the row you want to send. You want to send columns, number of items, right? You want to go across how many columns we have. In our Laplace code, it's going to be 1,000. And they're floating point numbers, and you want to send them to the up PE. And you can use an up tag if you want to keep track of things. There's other ways to do it though too. So there isn't just one way. For example, if you poke around a little bit, you'll see MPI has this nifty thing called MPI proc null, that if you send a message to proc null, it'll just go into a black hole. And you might say, why is that useful? It allows you to write nifty little pieces of code like this. You can say up is my PE number 1 unless I'm PE0, and then it's proc null. So PE0 doesn't really send an up message. And then later on in your code, you can just send all of your nodes send up, and the PE0 will just not bother sending a message that's going to proc null. And there's lots of different ways that you could do this. I suggest that you just use the basic sends and receives we've been doing so far and not get fancy. And tomorrow with the advanced MPI, we'll talk about ways that we could, deal with sending rows and columns and all kinds of other fancy user-defined stuff. But for now, it's just point at the beginning of the row you want to send, make sure you're sending 1,000 of them, and send it to the up PE. And boom, you've just done that part of our ghost exchange. You've sent some data up. You also want to send some data down, and you want to receive data. And so that's where the work is for you. So Fortran programmers, we're doing exactly the same thing. It's just now we're sending data in columns left and right because of the reason we just discussed. Same Halo exchange, same math. You just got to pay attention again. We're going to exchange data on these edges. So this PE wants to send row 250 to row 1 over here, and it wants to receive data or column, I should say now. It wants to send column 250 to column 1 over here. It wants to receive, no, excuse me, I'll get this right. It wants to send column 250 to column 0 here, and it wants to receive column 1 into column 251 over here, right? That's the math we want to do. So you want to make sure you get that right. And again, there's lots of different ways you might find as you're poking around to send and receive messages. But basically, as long as you point at the top of the column and send 1,000 elements, it'll send the whole row, and then you can receive it on the other side by saying, I want to receive 1,000 floating point numbers. So if you do this, you're going to find your code, starting with the serial code, is going to kind of organize itself into a very typical structure where the compute phase, where the number crunchings all happen inside of the plate, is going to be relatively untouched. We really don't have to mess with that at all. And the communicate phase, where we're exchanging these ghost zones, is where almost all of your effort is going to go. You're going to spend most of your time nailing down this communicate phase, making sure you get the indices right and setting the right rows. And you're not going to really have to mess with the guts, the science at all. And that's very typical of MPI codes, is the science remains untouched, whereas the communications is where the effort gets added in, and the code ends up with the compute phase and the communicate phase. That's very typical. As I said, though, we can't just constrain ourselves just to the computation part of the code inside of the while loop, because we've also got some other things out there. For example, the boundary conditions that we're setting. Right now, if you look at the logic for the boundary conditions, they just work on this 1,000 by 1,000 array. Instead, we now have 4 strips. You need to go and look at that boundary condition initialization code and make sure it does the right thing. So everywhere in our code where there's a temperature and a temperature last, we've got to go and poke our heads into and make sure we make any adjustments. This is a big deal, because it means that 80,000 line code before, I said it's really cool that we can take OpenACC and take an 80,000 line code. Somebody handed us. It's not even our code. We take that 80,000 line code and we either profile it, or somebody says, hey, here's the 200 lines of this code where all the action's at, all the math happens. And we could take it, stick in a few directives. Boom, we just sped up this 80,000 line code with a couple of hours of effort of playing with some directives, right? It's a big win for everybody. MPI, when somebody hands you that 80,000 line code, you got to say, ooh, what are the big data structures in this code that I got to break up? Because I got to go everywhere in this 80,000 lines and make sure I adjust anywhere that those things live. And this is the reason why MPI ports are so much more effort. And in our case, we'll see it with the Laplace code. You've got to dig into everywhere the temperature and temperature last live and make these adjustments. Okay, let's see. I'll answer some questions here before I continue on. Let's see. Okay, so Fortran is grandpa MATLAB in terms of noisy indices. Yeah, I mean, Fortran is more mathematical. Mathematicians favor the way that Fortran counts from 1. Mathematicians think it's absurd that computers count from 0 by default on indices, and that they work with column major for matrices. So it reflects the mathematical background. MATLAB, maybe it inherited from Fortran, or maybe it's just said we're going to do the more mathematical convention. Whereas programming languages, and the C programming language, that said we're going to count from 0, because that makes writing algorithms sometimes a lot easier to start from 0. There's lots of little tricks and stuff that rely on the fact that you're starting from 0, and they just chose a different order to churn through memory. And so that's the difference between Fortran and C. And they both have their virtues, but they both have their vices. And by the way, since most of the world of mathematical libraries, including the ones you use in Python or Java, were written in Fortran with some substantial number in C, this is where you'll find that people write wrappers to deal with changing the row major order of things around to make sure that they transpose things correctly. And when C codes call Fortran math libraries, in the documentation will say, yeah, recognize you're basically transposing things around. And that's why that transpose, that annoying transpose that shows up when you're using linear algebra libraries, this is exactly where it comes from. So, and we're comfortable dealing with it in the world of, doing high performance computing numerical methods. It happens, you come across it so much, it's a very common thing, and we're comfortable with swapping back and forth, but nevertheless annoying. Let's see. How would you send a 4x4 block instead of a 1x4 or 4x1 block? That's what we'll talk about tomorrow. It's easy to do, very easy to do, but I just don't want to overload. We're already doing a tremendous amount. Turning you into MPI programmers in a day. So we'll give us 2 days to turn you into advanced MPI programmers, but it's trivial to send a 4x4 block. I'll show you that tomorrow. We look at user-defined data types. We can define any weird shape we want. Very, very easy to do, but we're not going to dive into it today, tomorrow. Why in Python are both C and Fortran like arrays? Well, again, I guess I answered it. Okay, so there are a couple of options I give you to start this exercise with. You can start from just the serial code like we've been doing so far for the exercises, but I also give you a little bit of a head start with a template code. So if you're in the exercises MPI directory, you'll notice there's now this Laplace underscore template code, which just has some hints. And the hints are these things right here. So they're not valid code. You can't compile this code yet because it's got all these things in it. But these things right here, which give you some comments as to where you might want to stick certain types of things. So these are some hints, and you can use the template. You can even use the template for some hints and just start from the serial code and just start inserting things based on what you see in the template. So the template's meant to be some hints. Now there's also, there are solutions, at least my solutions, and yours may look different. My solutions for Fortran and C are sitting there. I would encourage you not to spoiler it for yourself and cheat, because if you can do this exercise, and I can't emphasize this enough, you are an MPI programmer. You are not going to accidentally do this exercise. It's going to take some effort and some work and some thought. No randomly trying and throwing MPI calls at this. You're not going to solve this problem. By the time, if you solve this problem and get it working, you're an MPI programmer. By the time you got this running, you have figured out MPI. You're not a master at it and proficient, and you still got lots of experience to help you get debugging and using other MPI commands and whatnot. But you understand MPI, and you should not be intimidated by anything with MPI. You just have to go and refer to the documents here and there for an MPI call you haven't seen before, but none of it will be that foreign to you. So do this exercise yourself for real. There is exercise time both today and your own free time if you've got it. I'm not assuming you do. And tomorrow we have exercise time to work on this. It may or may not be enough time for you to finish the problem. So we won't spoil things completely. Don't spoil it for yourself by looking at the solutions, because I really do encourage you to spend the time to do it. Some people that are really comfortable with C and Fortran already and working with code and the MPI, some people do this this exercise in a couple of hours, no problem. We used to do that real time, basically. We'd say, I think about 3 hours. We'd say, here's 3 hours, and a lot of people could get done in 3 hours. But there are other people that wasn't enough time for them. And that's fine. And so we don't spoil it for you. Take as much time as you need. You've got these accounts even on bridges for the next couple of weeks at the least. So if you don't get things done between today and tomorrow's exercise sessions, we're not going to ruin it for you. So please don't ruin it for yourself and give it a shot. So there are solutions there, though, if you want to look at them. But I encourage you to really pick your way through it and use the templates for hints if you want. And there are Fortran and C ones. But it is going to take some effort, because there are ways to go wrong here. There's two data structures that are big. You're going to have to break up, but it's not a mystery how to do that. I think we've given you a lot of guidance on that. And each one of them has the boundary conditions, and they have the ghost zones, and you need to keep track of that. You need to make sure you're sending, and receiving from the right places. Should I be sending from temperature or from temperature last? Should I be receiving in the temperature or temperature last? Which ones are the ghosts? So you need to think about these things carefully as you pick your way through it. Again, it's nothing new to real programming. You got to be careful in real programming. You don't just throw things out there and expect them to work. Well, that's not going to work. You're going to have to think about which things to use properly where. So anyway, it's easy to mix these up, and you're going to have to do a little bit of debugging here. And you don't have the benefit yet of the super nice debugger I'll show you tomorrow, but that's okay. This problem is fine to do with print statements and staring at it and wondering what you did wrong. So please, and there are multiple solutions too, by the way. So please give this some effort. Now, how do you know that it's correct? You might think that a very good indicator is that it works in 3,372 time steps. And indeed, I actually thought that was very reasonable myself when I first did this problem. I'm like, oh, it runs in the right number of time steps. It must be correct. Until I realized that there were still some bugs sitting around, and it still was finishing 3,372 time steps, which struck me as very coincidental and odd, until I realized what's actually going on in this problem. If we look at an actual graph of our solution for the Laplace code, so here's just a simple, terrible visualization of our Laplace code and the temperature gradient. So 100 degrees in this corner, and it's getting cooler as it goes out. Here's the working solution. And here's one that if I take the working solution and I just comment out all the MPI routines, here's what you end up with. And this actually doesn't look, terrible in the bottom corner where the PE3 here. Let me throw the PEs up here so you can see what's happening. So here's PE3, the bottom PE is solving things correctly, but you can see where they're supposed to be communicating with each other. It's a mess, and we don't get the right results here. So this boundary condition is still putting some temperature in here, but it's not lining up correctly. So this is the broken problem. But guess what? This one also stops at exactly 3,372 time steps. And if that seems, again, extremely odd and coincidental, the reason is that if we look here in the bottom corner of PE number 3, this is where, so this is the boundary right here. This down here is actually the DT that finally converges to cause the problem to quit. And that kind of makes sense. This is the hottest corner. This is where things change the most. So if you say what's the DT so far when we've been running our Laplace code with OpenMP and with OpenACC, what's the point that finally changes last that says, okay, we can quit, that causes the quit at 3,372 time steps? It's down here. So it turns out that even if things converge on a wonky bad solution because you've got a broken code, it still can converge in 3,372 time steps. So anyway, that's kind of a little bit frightening on this problem, that it can be so broken and still lead you to believe that it's working right because it's finishing in the same number of time steps. So a fix for this, if you really care, is you could print out the whole thing. You could dump out all the million entries and visualize it and go, yeah, you know, this is obviously a weird solution. This isn't right. That's one thing you can do. And for those of you that are comfortable with, you know, matplotlib and Python, or, you know, I think I threw this in an Excel spreadsheet at one point in time for some reason. I can't remember. That's what I think this is. But yeah, it's an Excel spreadsheet for some reason. But normally I just throw this in matplotlib and dump it up. If you want to dump out the whole thing and check it, that's fine. And that's not bad. But if you just don't want to get involved with graphics at all, you could just print out a magic point here. I picked the point like right here and said, if this point is really 0, then things are broken. It should really be about 1 degree out here at 900. This is 900 down the grid, or 750 down the grid is the break point right between the PEs. So it's about 750 down, and it's about 900 and so out. So I picked the point right there, and I said, if that point, this magic point right here, is equal to 1, that's probably good. If it's not, something's probably broken. So here's a very simple check you can do if you want to see, without getting involved with visualization, if you want to check and see if your code is actually working correctly. Because like I said, this is a weird case where 3,372 time steps to convergence does not necessarily mean your code's working well. So anyway, beware of that. Okay, this I talked about already. I said we're not going to spoil with the exercise review tomorrow. We're going to talk about this and maybe some extensions to this and ways we could apply some of the advanced MPI stuff we'll talk about. But we're not going to just throw a solution in your face and ruin it. So if you don't have time to finish the thing, you know, today or tomorrow's exercise time, don't give up on it. Continue to plug away. Okay, so here to sum it up is our exercise. And our exercise, again, you've got the serial codes to start with. You've also got the template codes to start with, and which have the hints in it. You've got some MPI documentation next to you as you work your way through it. As you compile, we're just compiling with a normal compiler. You want to run it, we're going to make life simple and just say we're only running this on 4 PEs to keep the logic simple. And you have the solutions out there if you really get desperate and really want to take a peek. So with that, we're going to kind of officially do a combination of starting on exercise time. Also, for those of you that want to work on the exercises later or whatever, we can call it the end of the day for you. We don't have any more material today. It's exercise hands-on time. So you can leave if you'd like to. But I do suggest that you find the time, sometime at least, even if you do intend to work on this over the next week or something, at least dig into it while you've still got us here to answer questions for you, you know, and serve as TAs. So dig into it as much as you can between this afternoon's time and whatever other time you have and tomorrow's exercise time. Okay, with that, I'm going to turn to questions. Again, those of you who want to call it a day, you're not going to miss any more MPI content. But tomorrow we are going to start on time because we do have a lot more MPI stuff to cover, because advanced MPI has a lot of really amazing nifty features to make life easy for you. I've hinted at a lot of them already, and we'll cover those. And then we're going to talk about some of the tools that also make life easier for you. And then we're going to wrap things up and also talk about the things that we didn't cover this week, like people have mentioned other programming languages and approaches, and we have a lot of that in the outro talk. So that's the theme tomorrow. So, okay. So again, those of you that want to bow out can do so, but I'm going to answer any pending questions here and hang out and help people during exercise time. Let's see. At MPI barriers are kind of pooling mechanism. Writing an MPI barrier is actually is a tricky thing to do. Making a, not just MPI, writing barriers, implementing a proper barrier is a tricky thing. If you look into it, there's a lot of subtleties to it. It turns out also to be such an important thing, because barriers are fundamental to this, that usually barriers are, believe it or not, implemented in hardware. Most serious networks these days have the ability to implement barrier at the hardware level. The network interfaces can confirm a barrier across the entire network of participating nodes. But doing a barrier, just creating even software with multiple cores to make sure a barrier is good, both efficient and also bulletproof, trickier than you think. So these days, most barriers are a part of the networking hardware, and MPI can take advantage of that. Let's see. Okay, the reservation invalid thing, I'm sure Tom is on top of that. Well, yeah, was that Excel? Yeah, that was Excel. The time I put that slide together, I guess I can't remember why it was the easiest way to visualize that. I just threw all the data in Excel. By default, I use Matplotlib for almost everything I visualize anymore. How do you know the magic point without the visualization? Well, you don't. The magic point's a little bit of a cheat. If you were doing this as a real scientist, you're writing a code from scratch like this, man, you better have some good visualization tools at your disposal. And we'll find the debugger that we use tomorrow actually has some nice visualization built in. You better have some good visual. Actually, I wonder why I didn't use the debugger to spit that graph out. I can't even remember what my thinking was at the time. I'll show you some visualization with the debugger of this Laplace code. But when you're working on codes like this, you really do need some good visualization tools to say, is my code behaving sensibly? Because with gigantic distributed data structures, there are no magic points, and it can be very hard to know what's going on unless you do have some good visualization. Let's see. Looks like there is MPI for Python. Yes, there is. There is an MPI wrapper for Python. We'll talk about that tomorrow. It's got some limitations to it, but the guy who did it has kind of shifted jobs. So I don't think his support is what it once was, but it's pretty nifty. And I use it in one of my computational physics classes. So I will talk about it a little bit tomorrow. Pure work, arbitrary. In the real world, it's not for a person asking about a number of to make a code work with arbitrary PEs. Do you start hard coding and then kind of expand it out from there? Now, generally, once you get a little experience, it's just as easy to start writing a code and say, I'm going to build the flexibility into it, like our Pi integration solver did. I mean, just from scratch, you build it and say it can just adopt to the number of PEs that are available, adapt to the number of PEs that are available. And that's typically when you write an MPI code where you start. Just for the sake of keeping our example simple and streamlined, we haven't done that here. We've kind of hard coded in some limits. But if you were really starting a project from scratch and you were writing the MPI code right from the get-go, you'd probably say, okay, I'm going to make it flexible to the number of PEs that are available. Although sometimes there are reasons why people will have some constraints. For example, if you've got a code that uses FFTs, which is a lot of codes, even if it's like a numerical simulation code, but you're using that as part of your differential equation solution, you might restrict people to powers of 2. So it's not uncommon to find a package that says you must have your dimensions for your problem must be powers of 2. So you will see constraints, but usually that's not because somebody hard coded it at the beginning. It's because that just makes life a lot easier for their math and their domain decomposition. Presentation starts at 12:30 p.m. tomorrow according to schedule. No, I think we start at 11 with exercise. Let's see, exercise time. So 12:30 for the first presentation. So those of you that aren't interested in any support can show up then. Let's see. Let's see what does NPE stand for? So NPEs is the number of PEs that the code is running on. In this case here, I think the logic that I've got there in that template is since we're sticking ourselves on 4 PEs, it might be nice to verify that it's only running on 4 PEs in case somebody tries to launch it on the wrong number of PEs. Since our logic isn't very flexible here, since we're being a little bit hardwired with our logic, it might be nice to check that and say, okay, is it on 4 PEs? Save somebody from trying to run it on 7 PEs, and then your code does weird things. What is the advantage of running a Laplace code with MPI compared to OpenMP and OpenACC? This is very, very important message. I can't repeat it enough. This code is going to be scalable. This code could run on 1 million cores our OpenMP code is restricted to never running on more than a single node of cores. And you might get a very big, fast node with 256 cores in it. Those are out there, but that's it. That's the limit. You're not going to run on, and even there, the memory contention issues are terrible. So there's a limit with OpenMP. You can only use the maximum number of cores you can get on a single workstation. Might have 2 processors in it, or maybe even 4, but that's it. You're not getting more cores. You can't run across workstations with OpenMP. OpenACC is the same thing. It runs on the GPU. Doesn't run across multiple workstations. If you want to run across more than one workstation, you need MPI, and that's where this solution is more painful to implement, but can scale infinitely. We're not really interested in scaling 1,000 by 1,000 plate infinitely, but we could turn this into a 1,000,000 by 1,000,000 plate and have no problem running it on bridges. Big data course, we talk about Apache Spark. Yeah, we use Spark a lot in our big data course, and that is a very different approach to working in parallel with data. A Spark you can think of as more of an application. Spark is a fancy application that allows us to work in data in parallel. And behind the scenes, Spark does tons of parallel stuff like we've learned about this week, but it's an application that uses it. It's less, it's not really as much a programming in language or environment. So you hope that Spark has all the right tools to attack your problem, but it's not really, with the parallel programmers or people that did Spark, not you as the user of Spark. So Spark is for manipulating data. I mean, you might say, of course, everything's for manipulating data. I mean, more in a sense, more in a classic, databases. It's not for doing Spark is not for doing simulations. It's for just shuffling data around, which is mighty important in the world we live in, but it's not generic scientific applications. That's a good point. One sanity check, you could verify the symmetry. Although the approximate's the hard part, you'll find the temperature values are pretty small in the middle, but yeah, that's not a bad way. You could try to look for the symmetry because there's a symmetry axis for our problem, the diagonal. So you could look there. Certainly when you visualize it, if there was an asymmetry in the visualization, immediately you'd know something's wrong. Well, exact. So shouldn't the symmetry be exact? Exact is a dangerous word to use with floating point numbers in computers. For example, you never ever want to compare floating point numbers with equal. So if with an equal sign, you never want to say, is this floating point number equal to that one? Because the answer is, well, you don't want. I won't dive off and do a big thing about that, but that's just general principle. You never want to do it. Because floating point numbers round off to half bits. There's all kinds of subtleties. Floating point math is a fascinating topic, but the more you study it, the more you realize how many pitfalls and dangers there are. And so if I were to say, take the topmost point in our Laplace, the bottom left corner and the top right corner of our Laplace code, they should be equal to each other. But for what definition of exact? If I say they're exactly equal to all decimal places of a 64-bit number to the last bit, that is probably not true. Matter of fact, I bet money that's not true. And so you can't compare them exactly. Instead, you'd have to approximate and say, okay, well, that means we just need to round them off. We need to see if they're equal to, well, how many decimal places? Now we're thinking, okay, is 1 decimal place, 2 decimal place, 3, how many decimal places mean they're equal to each other? And so you could come up with an answer, you could come up with something that works, but it's not as trivial as just comparing, because mathematically it's an exact symmetry on paper, but computationally, exact is a dangerous word to use with floating point numbers. When MPI work with program run on a single node. Oh, absolutely. MPI this is another thing I'll come back to. I'll talk about now since we have the time. MPI to run on a single node is not only fine, but it can even beat OpenMP. This actually surprises people a whole lot. I won't go on too much about it here because I will talk about it when we have the whole audience later, because it's an important point. People often say, okay, well, if I'm only running on a single node, then OpenMP, which is the right tool for that job, is going to be the best performance. And then they take an MPI code where somebody's gone to that extra effort, they made an MPI code, and they run on a single node, and they treat the cores as separate ranks, separate PEs, and they find out that the MPI version beats the OpenMP version, and people are surprised. It's not an uncommon thing to have happen. And the reason for that is that all this extra effort you're going to an MPI to do the domain decomposition so that it'll work on distributed memory machines, also very often has a positive effect on breaking things up across caches, avoiding cache conflicts. And so even though MPI running on a single workstation by itself shouldn't have an advantage over OpenMP, that domain decomposition often does some nice things with cache optimization. And so it's not uncommon at all to find out that a pure MPI code beats a pure OpenMP code on a single workstation. Now, the reason that you would never, if I'm only interested in running on a single workstation, though, I would very rarely want to put all that extra effort into the MPI port. Instead, the OpenMP one's going to give me a huge payoff quickly. So, but once you've got the MPI code, running it on a single workstation is often a very optimal thing to do. Question is, it seems in the hint PE0 is given special status. Well, as we'll find very, very often in MPI codes, it just makes sense to have a particular PE be the manager to take care of things like input from the user, right? You don't want the user, all the PEs asking the user how many iterations to run, right? So you need a special PE. PE0 is always there. You know, since we start counting from 0, there's always a PE0. So it's very common to find that PE0 is just implicitly becomes the manager, the supervisor PE. And that way, if we run on 4 nodes, PE0 is in charge of the other 3. If you run on 4,000 nodes, PE0 is in charge of the other 3,999. So PE0's special status as the supervisor just kind of naturally arises. It's always there. One needs to worry about memory available to each PE while using MPI. This is true. This is true. You always need to worry about how much memory is available. So if you start running if you run MPI on a single laptop with a bunch of processes, they're only each going to get their share of memory. So on the other hand, the whole reason of going to MPI is if that's not enough memory, well, with MPI, grab another laptop, your friend's laptop, and connect them together with MPI. Now, in reality, you probably just move to a better workstation. Point being, with MPI, if you don't have enough memory, scale up. You have an out. For an MPI code, if you don't have enough memory for your problem size, you just grab more nodes. That's the whole point of MPI, is you can keep scaling up. And if your department doesn't have enough nodes, that's why you apply to XSEDE and say, I want an account on one of your machines. We've got more nodes. And there are bigger machines in XSEDE for people that need even bigger amounts of memory. So that's the whole point of MPI, is when you run out of memory, just grab more nodes. My comments about OpenMP, MPI, and cache use optimizations. I'll repeat them again, although you're gonna hear them again tomorrow, because for everybody's benefit, because I do have it in, I think, the outro talk. But the magic thing that happens, can happen, is that when we're doing this domain decomposition, we start breaking our data structures up into pieces. That can very often avoid cache conflict. So if you're familiar, I'm going to assume you're at least vaguely familiar with caches and how they work. Caches work by mapping you have a small cache and a big memory. So caches work by associating each line in the cache with certain lines in memory. And so something that's big and spans across memory can be fighting to use those same line of cache. The big data structure will be fighting to use the same lines of cache. That's not an uncommon thing. And those cache conflicts then can slow your code down. And there's different ways to address that we don't go into in this course, because we're not about serial code optimization so much. But in the process of taking that big chunk of data and breaking it up into 4 chunks of data, you can often move them around in memory in a way that there's less cache conflicts. And that just happens serendipitously because things aren't contiguous in memory anymore and under the same memory management scheme, because they're separate isolated processes. And then all of a sudden, your cache performs better. And so it's not a huge effect typically, it's just a couple percent, but nevertheless, people go, why is my MPI code, which is written to run on a distributed memory machine, running even a couple percent faster than my OpenMP version of the code, which is only supposed to deal with shared memory machines? So isn't OpenMP the exact right tool for the job for shared memory, and somehow MPI is beating it at its own job? And so that's because of that cache thing. And it's not a big deal, because you don't put the effort into the MPI code just to gain that 1 or 2%. It's a harder port. The OpenMP one, you're happy to give up that couple percent just to have such an easy port. But once you've done the MPI port, because you need to scale it up, so sometimes the benefits you get when you run that code then locally on a single node. How can we communicate between PEs working on different laptops? Well, when you build your MPI cluster, if your laptops are on your network, and it can be any network, it could be your home Wi-Fi network, when you install MPI, it allows you to name hosts. So I just named this laptop as a host and that laptop as a host, and now they're both part of my MPI cluster. So building your own cluster, you can glue them together with whatever you want. Now, the communication performance, if I just did what I talked about, used a couple laptops on your home Wi-Fi network, your communication bandwidth is going to be, your terrible Wi-Fi bandwidth and latency, but it'll work and your MPI code will run. So MPI is happy to assemble a cluster for machines scattered anywhere in the world. I mean, I could start a cluster right now. I could use my laptop in front of me and tag some machine from our machine room at the supercomputing center. And my third node could be something in some Amazon cloud somewhere if I wanted to. And the MPI is happy to make that into a cluster. And then when I run my MPI Run, it's using all three of those nodes. So, and again, it would be a weird, bizarre, terrible communication performance, but MPI doesn't care about, that in terms of making the code run. It'll just perform terribly. How can we compile an OpenMP program wrapped with MPI? Well, if you try the wrappers we're using right now, like MPI CC, they're happy to take the -MP flag. So the MPI compiler behind it, as we said, it's really just a very simple little disguise for the regular NVIDIA compiler, which we've been using with OpenMP the past couple of days, right? So we'd have no problem. You can take a code and use this MPI compiler, and if you have some OpenMP directives in it, you can add them in -MP and it'll compile just fine. So I'm answering your question about how to compile. Now, how to actually make those things work together properly, I'll save for tomorrow when we talk about hybrid computing, but they work very easily together. But there's no problem once you've written a code that uses both OpenMP and MPI, or OpenACC for that matter, no problem compiling them together. Just add in the -MP flag to this MPI CC. Oh, it'll be happy to compile OpenMP directives in there. Besides using GitHub, what's a more efficient way of moving data? I would not recommend going through GitHub. I mean, there's no point in that extra step. You can move data onto and off the bridges from your laptop. Somebody say you have a personal PC with just SCP. SCP is fine for gigabytes. If you're going really huge and you want something that's for huge amounts of data that might take days to complete, and if there's an error or a timeout that can recover, then there's something called Globus, which excels at that. But Globus is a pain in the butt to set up. You got to set up certificates and everything else. But Globus would be if you said, okay, I really want to move, terabytes of data. I've got a pathetic network connection that times out all the time. That allows you to robustly move things. But for just gigabytes, I myself would just, of the many alternatives you have, if you look on the Bridges user pages and user guide, it gives a long list of ways to move data. I would just use SCP. I think that's if you're not familiar with it, the SCP command line art command that you can use within any Unix shell is a simple way to copy files from across different machines. And it's fine with gigabytes of data. And that's what I would do, SCP from my PC and I do it all the time. That's what I do use when I go between my PC and my and Bridges. And sometimes I even use it. I'm on Windows mode. There's a free Windows utility called WinSCP, very popular. That's graphics. So if you're using a Windows PC, they might even have versions of WinSCP for Mac and Linux. I think they do. So WinSCP is a nice GUI based one. I can just drag and drop with my mouse files back and forth between Bridges and my laptop. I use the command line version of SCP though all the time. Let's see, question here about in the MPI template, I use the serial code timer. That's strictly because it's sufficient here and that it's, it stays close to what we were doing in the serial code. But the MPI does have a fantastic timer. I even take a second to talk about it tomorrow in advanced talk just because it is nice, and MPIW time. It's a fantastic timer that is microsecond or better accurate than everywhere. So if I'm writing an MPI code and I'm sticking in timers, which I do all the time, I stick lots of timers in my code to make sure performance doesn't do something weird as somebody moves to a different platform. I use MPIW time. And I highly recommend it and suggest it. I just didn't want to, to introduce anything unnecessarily here, but because the regular timer is sufficient for our purposes at the moment. Let's see. Don't have to apologize for going back to other material. That's fine. However, I'm not sure why your compiler is not recognizing MP flag. First of all, MPC++. So use the regular. Let's see. I don't know if the C++ compiler is wrapped any differently. I don't think it is. I'd have to run. I'll try some tests here after in a moment here myself. But look at the man page for it. and see what it says. I don't think it should care about the MP flag, but do make sure you're using the right dash. If you're cutting and pasting things from PDF files, use the right dash, or that will cause problems. But I'll take a little test myself in a moment when I get a moment. So MPI CC and MPI Compiler standard serial wrappers to find the required MPI libraries. That's exactly right. There's nothing more complicated than that. They're pretty lightweight wrappers. All they're doing is finding the right libraries, and that's it. And and the right header files. That's pretty much it. And you can see that too. If you type like MPI CC -B to find the version of the compiler flag, you'll see. In this case, it'll come back and say, hey, I'm just a regular NVIDIA compiler. If you do it on any other MPI installation, it'll come back and say, I'm just a GNU compiler, or I'm just the Intel compiler. So when you look at the version of the compiler, it'll let you know it's just a generic compiler. Which MPI function should I use to initialize each PE? I'm not sure exactly what you mean by initialize here. If you call MPI init on all the PEs, call MPI init like we've been doing in all of our examples so far. That's all you need to make sure MPI is up and running on each PE. So a wrapper just is a mixture code wrapped around other code. Yeah, that's exactly the right way to think of it. And that's not unique to compilers here. There's wrappers on all kinds of stuff all the time. A lot of Python interfaces, for example, to other libraries are just a wrapper that just reshuffles a couple of parameters around so it can call something else in some other language. It's a wrapper. People use the term wrapper even in their own code. If they have a routine somewhere and they want to change the interface to it slightly or a little bit, you can make a wrapper that just changes the interface, just does a minor thing and passes it along to the real routine behind it. That's probably the most generic term for a wrapper. In coding, it's usually used to say you're going to do a little bit of manipulation and then pass it along to something that's really behind it. In this case, we just set up a couple paths, to find the libraries and to find the header files, and then pass it on to the real compiler. Yeah, it's absolutely the case. If you don't have the module loaded, then you won't have the compiler loaded. But since he's saying it's not recognizing the flag, I think if that's the case, it's a different problem. If it's not recognizing the compiler at all, then you don't have the module loaded. I just pulled up the documents for the NVC++ compiler, and it confirms, yeah, I should just use the -MP compiler switch. Should work just fine. And I just gave it a quick test with the NVC++ compiler on our Laplace OpenMP code, and it did compile and run just fine with the -MP flag. So maybe you don't have the module loaded, but then it should just say you can't find it. So, but it does work. So make sure you're following our instructions and just substitute ++ after we've been doing the NVC, and it should work. For the MPI broadcast, you're using to send the max iterations to the other PEs. Should it be an integer value? Well, no, it's not the number of PEs you're not sending out. You're sending out the number of iterations that the user's inputting. So this is where the user says, 4,000 or 1,000, and that's what you're broadcasting to the other PEs. Oh, well, I answered your own question. You answered your own question. We're good on that question. Why does your program become much slower? Well, somebody else says if you spread it out over other nodes, latency is an issue. So if typically it's faster to run with all the PEs being on the same node than spreading them out and having them, you need to connect it over the network with that latency that's involved. It's quiet enough. I'm going to slide over to my adjacent workstation. I'll be monitoring the chat channel, and I'll be right back if some questions pop up. Oh, I'll answer one question before I do that here. In our example here, we're hardwiring in the number of PEs, and then we're forbidding the user from running on anything other than 4 PEs. So that's kind of the logic that's set up right here to guard us from having anything weird happen. So we defined in the number of PEs as 4, and then we're saying the user had better not try to MPI run with anything other than that, or we'll warn them. the math to initialize the boundary conditions takes a little bit of thought. I don't want to spoil it for everybody and endorse what you got or not, but you're on the right track. I'll say that. Yeah, feel free to do anything you want if it's not the right number of PEs. Yeah, you can quit and return one's a pretty reasonable thing to do. Oh, the question about Expanse nodes out there. If you go to the XSEDE website, Expanse is part of XSEDE as well. If you go to Expanse or the XSEDE website, you can see the comparison between all the different machine capabilities. So they're all awarded from the same place. XSEDE, directs awards towards different platforms. So you should have no difficulties going to XSEDE and finding out which machine best fits what you're trying to do. And on that note, everything we've done here in this workshop should work on not only Expanse, but pretty much any normal computing environment you're trying to come across. I've gone to great efforts to make sure we don't have any platform specific stuff in here that doesn't absolutely have to be here. So you should be pleasantly surprised as you move to other platforms in your department, other XSEDE machines, or anything else that there's very little platform specific stuff that we've gotten into here. Yes, I can confirm your confirmation. The NPEs are the number of processors, as in previous examples, right? Number of ranks, number of PEs, however you want to call it. It should be 4. We're keeping life simple. It's 4 everywhere. You just want to verify it's 4 when the code starts, and it will be 4 the rest of the code. And since we are breaking the metal plate up, the main data structures in our code are getting broken up into pieces. You need to go everywhere where those data structures live and make some adjustments, and that includes the initialize code. I'm not going to answer yes or no on exactly what the math should be for these rows because I don't want to spoil it for people. It's partly the hardest part of this is making sure you get that right. So I don't want to spoil it for everybody. When you want to receive, the ghost row is obviously going to be the outermost row of the remaining piece of your metal plate. So it's the outermost row. Just think of it that way. I suggest that the best thing to do is to get a piece of paper out and sketch out exactly, what the section of the plus, the section of the metal plate looks like, and get the indices nailed down on paper in your head before you can start trying to code. Because this is most likely place for people to go wrong. Well, folks, it's been quiet for long enough right now. We're down to, it looks like 40 some of us. So I am tempted to let Steve get on with his day unless there are any more questions besides this last one here. So we'll give it a minute or two and then we'll maybe quit a few minutes early. We're almost there anyway. Let's see, can a tag argument be any number? I think it's limited to be, I want to say 15 bits up to 32,000 something. It's a very large number. So you're not going to run out of them if you're doing anything manually by hand. I think it's an integer up to 32K. I believe it's something very large, but yeah, so it can be pretty much any integer you're going to write in your code by hand. Oh, see, question about defines. Yeah, defines are, I'll oversimplify a little bit, but you'll be fine with it if you're not really a C person. Yeah, you can think of it as it's a global persistent variable. It actually is a macro that's an outright text substitution in the code. So what it really does is it goes through the code and does a text substitution everywhere it sees row, it sticks in that number. So it's literally like editing your code, but you can just think of it as a global variable, would be fine. You're very welcome. Thank you all for your attention today. And we'll have plenty of, we'll let Steve off the hook a few minutes early here. We'll quit because we're going to have an exercise session starting tomorrow. So tomorrow at 11 Eastern Daylight Time in the United States, we are going to have plenty of hands-on time too. So I don't feel like depriving you of a few minutes here. And for those of you that don't care for the exercise time, you don't have to show up until our first lecture at an hour and a half later. So, okay, well, thank you all.